We're ready for our next session of talks. Session 4, this is functional surfaces. I hope everyone enjoyed a lovely lunch. And I'd like to introduce our first speaker today, Professor Alison Davenport from University of Birmingham, who's going to shed some light on localized corrosion.
Okay, well, first of all, I'd like to thank the organisers for inviting me to what's turned out to be a completely fascinating conference. And secondly, I'd like to offer huge thanks to the very large number of people who have contributed to the variety of experiments that I'm going to show today. So what I'm going to talk about here is to look about the corrosion of metals. And as you can see here, there is a whole variety of different types of corrosion, and we get some pretty curious types of corrosion sites. So essentially what I want to show you here is that you can see some pretty strange shapes here, some round, some rather strange colours and so on. And what I want to show you in this talk is how these kind of strange structures arise and why the fact that they have these kinds of structures is important. And the other thing that's really key here is that we need to be able to see how these things develop in wet environments and characterize them. And to do that, we need in situ characterization. And so a lot of the work I'm going to be talking about is using high-intensity X-rays at synchrotrons, where you have lots of different lovely beam lines with a whole variety of techniques, including imaging and diffraction for characterizing materials. But I'm also conscious there's a lot of people here not hugely familiar with the basics of corrosion, so I thought I'd start with something that you're probably all familiar with, and that's what happens when you put a bit of a rather reactive metal, sodium, in, whoops, hang on. When you put a little bit of sodium into water, and that's corrosion of sodium, and sodium dissolves directly in water, liberating electrons which get picked up by the water, and we generate the hydrogen bubbles, and it goes fizzing around very, very vigorously. So that's what we call active corrosion. However, magnesium is also a very reactive metal, but when we put that in water, it's not quite as reactive. You can see you do have quite a decent number of bubbles coming out the top, but nothing like the vigor with which sodium happens unless you scratch the surface, and then the rate of attack goes up a lot faster. So what's happening in the case of sodium is you've got here the metal atoms dissolving away into the electrolyte, but in the case of magnesium, you've got a passive film forming. What happens is essentially the metal ions go out, they meet the water, and then the water forms oxygen ions, and those under the electric field at the interface, because it's all electrochemistry, they exchange places and start forming a skin on the surface. And metals need a skin to protect them from the environment in the same way that we do. And of course, if we scratch our skin and damage it, we get a bit of bleeding, think corrosion, and then after a bit of time, you regrow your skin and things get better again. And so this is the basis of all the things that I'm going to talk about here. So I had a very early interest in my career in what passive films were actually made of. And so I ended up doing some synchrotron experiments where we took a single crystal of iron in an electrochemical cell where we were able to reduce off the existing passive film and grow a nice new one, and then do some very careful diffraction on that, and we could tell that we had a thin film which is about 3 to 5 nanometers thick. It's about 20 atomic layers, but it's more than plenty for you to be able to see nice shiny steel when you wave it around in a wet environment. And this also has a very nice spinel structure. The key thing here, though, is that I was really interested in is that there is good epitaxy between the spinel structure and the metal underneath. So if you think of the idea of the metal ions going out and the oxygen ions coming in, it's a pretty easy process if they don't have to rearrange themselves or nucleate and grow, which suggests that these things can grow really pretty quickly. So in fact, this is based on my PhD work, this knowledge of fast growth of passive films, because I spent a lot of my time scratching bits of metal on a rotating disc and measuring the growth of the passive film on the surfaces. And when you actually scrape a piece of metal under electrochemical control, you can see the oxide film starts to grow very rapidly, and then as it grows thick enough, it switches off the current completely, everything stops happening, and that happens in milliseconds. So the growth really is fast, and then I got very carried away when I was doing my postdoc. We had a thin film of aluminium deposited on a silicon wafer. We stuck it in a beaker with some electrolyte and a puddle of mercury at the bottom, which we could use to measure the currents very, very fast with a very low impedance system. And essentially, what we found out was that we got repassivation in tens of microseconds. So an incredibly fast process, and the current densities that we were measuring in this very carefully designed system was 200 amps per centimetre squared, which anybody doing electrochemistry will know is quite high. So we've got this very, very fast and efficient process for producing this nice skin on metals. And that's jolly useful because we go flying around in aluminium aircraft. And so we rely to some degree on the fact that to a large degree on the fact that these skins form and reform very, very easily so that we can use aluminium in lots of practical applications. However, things can go wrong, and there are circumstances where localized corrosion of aluminium can develop, and the consequences of this can actually be really quite serious. This is a fortunately very rare example of where a bit of localized corrosion of a fuselage produced a hole that was big enough to initiate a fatigue crack, and part of the fuselage was lost. So to avoid things like this, all of the people who operate planes have regular maintenance intervals to make sure that they go around and inspect the plane and check it for corrosion, just to try and prevent these things from happening. But of course, they're very much interested in trying to make the maintenance intervals longer, because that's more efficient in terms of availability of planes and everything else. And so there's some interest in trying to develop corrosion prediction models. So, spoiler alert, what I'm about to tell you is that that doesn't work very well for reasons which I hope will become apparent. So, essentially, the kind of corrosion that we're dealing with is known as atmospheric corrosion. We have salt from the air or sea or whatever deposits on a metal surface, and then what happens is we get a bit of humidity, the salt deliquesces, we've got a droplet, and corrosion happens underneath the droplet. So we wanted to study this process, and the way in which we did this was to take a little rod of aluminium alloy 2024, which is common fuselage alloy, and we turned it down to a 1 millimeter pin, and then put some silicon tubing on there, a droplet of salt water, carefully controlled the humidity, and put it in a synchrotron and watched it corrode. So we've got X-rays going through the area around the droplet so that we can see the corrosion developing. And that's a horizontal measurement through a tomogram. What happens is we rotate it by 180 degrees and then draw together all those images and come up with a three-dimensional tomogram. This is a horizontal slice through the pin, and you can see the little white particles are little lumps of alloy constituents, copper-rich particles, and so on there. So each rotation took 5 minutes. So what we did was continuous rotation of this pin, continuously measuring it and watching pits develop on the top surface. So what I'm going to do now is to show you a video of that process, and I'm going to show you a video where we rotate. This is the top of the pin, and this is the first pit here, and this is what it looked like. The gold bit is the pit, and the blue bit is actually a hydrogen bubble, because these tend to form when you get this fast burst of dissolution when a pit happens. And this one a bit later on. That's the big one that we got at the end, and you can see here that that's the pit, and that's its rather larger hydrogen bubble. So let's have a look at the video. You can see this is the pin. We're zooming in on pit number 1. Then we've got pit number 2 here with its bubbles again. And there you're going to see pit number 3, which starts small and then carries on growing, and it gets bigger and its bubble gets a lot bigger. So you can see this is over a period of 90 minutes. You've got this successive process of little pits growing and then mostly stopping, except number 3 carried on rather vigorously. So what I'm going to show here is some careful work trying to determine what the shape of the pit was at each, pit number 3 was at each stage. And you can see here that you can see here that the pit is kind of long and thin, but it's not uniform in shape. It's kind of all jaggedy all over. And then that's the first measurement. The second measurement, we've coloured the growth in a different colour so that you can see how it grows successively. And you can see that some bits haven't grown at all, and other bits have undergone quite vigorous attack. And so this is the video, another video. I think we might need a bit of intervention there, I'm afraid. So the other video, you can see that's number 1, that's number 2. You can see this big lobe coming out here. And then as you see these gradually develop, you'll see how tremendously variable it is, which bits burst into action and which bits decide they're not going to change at all. So you can see through the course of this quite a lot of varying development there is of this particular structure. So let's think about the implications of this. We can see here that we're getting these sudden bursts, and these bursts themselves, for example, this step of 20 microns in 5 minutes, that corresponds to 0.2 amps per centimetre square, so that's 1,000 times slower than passive film growth, but it's still fast enough that if you relate it to how fast it would be if it grew that fast in a year, it'd be 2 meters, which we kind of notice on an aircraft. So you can see that the aggregate growth of these things is based on this very, very intermittent process. And that's why measuring it is going to be very difficult. Predicting it is going to be very difficult. Well, to explore what I think is happening, I'll jump a bit later on, but what I'd like to do is to give you another example of a different system where corrosion prediction is actually desirable. And again, this is nuclear waste storage. There's a lot of intermediate level waste containers being stored above ground, and they're hanging around probably for the best part of 100 years before the UK has a fully operating geological disposal facility. So the question is, do we just leave them there, or is there a risk that they might start corroding? And if they start corroding, when we come to pick them up, or somebody later comes to pick them up, they might break. So there's, again, an idea to want to be able to make long-term predictions of how corrosion is going to behave. And so in order to take this forwards, quite a number of people had a look at well-known behaviour of corrosion pits in stainless steel. And Roger Newman had a very big interest in this, and pointed out that there's this very curious type of corrosion in which you get a metal pit forming, but it has a funny looking top. If you see here, it looks a bit like a colander. It's got lots of little holes in it. And how on earth does that develop? So he came up with a proposal that you get a pit growing normally, and then you get some lobes swinging out to the side, and then they swing out and pop through the top. Now this sounded sort of kind of implausible, but you know, it's a bit hard to follow. But we decided one way to do it was to try and do it in 2 dimensions. So I took a very thin foil of stainless steel, so it's like a 2-dimensional metal, if you like, it's about 50 microns thick. Embedded it in epoxy, snipped the top off so we got a nice clean electrode, and essentially did some synchrotron radiography on it. And I'm going to show you a video of how, and we put electrodes in and so on. And I'm going to show you a video of how these pits grow, which I'll explain first of all. So again, spoiler alert, Roger was right. You can see this nice lobe here on the side of a pit, and it looks like it's going to come up and pop the surface, which is, my video is working, exactly what we can see. This is 40 times, but you can see that you get these nice lobes coming out the side, popping out the top, and making these nice little holes on the top of the metal foil. So a very curious mechanism. Again, we've got this situation where localized corrosion is not behaving in a simple, uniform fashion. So to be able to get our heads around it a bit, I'll go a little bit into the basics of corrosion, if you'll bear with me. So essentially, what we've got is, what I've got is a pit, and what happens is that the metal dissolves within the pit. M is a generic metal, producing metal ions and electrons. The electrons go to the outside world where the cathodic reaction takes place, which is usually reduction of oxygen on the external surface. And then what's really important here is the conductivity of the solution, because if this is fairly conductive, then you get more of the interfacial potential drop across that interface rather than going on within the pit itself, but I'll have more of that later. So essentially you've got this pit, and the important part here is that when metal ions meet with water, they undergo this process called hydrolysis, which is where we produce a lot of metal ions. A lot of hydrogen ions, so we end up with an acidic solution, and this is bad because acidity dissolves passive films. So I think you can see where this might be leading. So where we've got an acidified, concentrated solution inside the pit, it's really hard to form the passive film here, so that is where the corrosion process actually takes place inside this funny shaped hole. So the other thing that is also important about how pits grow is how much of a driving force you've got in order to produce these, oops, sorry, this is difficult because the 2 buttons are very close. So you can see here, if you can produce metal ions in the cavity fast enough, faster than they can escape and diffuse away, what's going to happen is you're going to supersaturate the solution with the metal salt, and you'll get supersaturation, and you'll have a salt layer crashing out on the bottom surface, and this has a bit of a resistance, which puts the brakes on a little bit in the production, and so that will leave you with the rate of production being equal to the rate of diffusion. So it's a way of putting the brakes on if you've got a salt layer. All very nice in theory, but do we have any evidence for the fact that things are controlled in this particular way? Well, these are a couple of stills from pits. We grew lots of pits. One that was grown at a low conductivity and one that was grown at a high conductivity. And you can see that for both of them, we would expect the driving force for electrochemically controlled dissolution to be higher if you've got a more conductive solution. But in fact, you'll see that the depth of the two was the same after growing after 60 seconds, despite one being low conductivity, the other one being high conductivity, which is very much consistent with the idea that the diffusion is doing the job, and this is rather telling us that we probably have salt films at the bottom of these layers. So we can also see what we expected to see, which is that if we've got a solution concentration, if we've got a solution concentration that is higher, you can see here that the pit's wider if you've got a conductive solution, so there's a bit more potential across this interface, so it can go faster, whereas this one's a little bit narrower. So this really suggests that we've got electrochemical control on the sides and diffusion control on the bottom. But do we really produce salt films? Well, so then we had a play to see if we could see salt layers, salt films. So this is an example of nickel, a ribbon of nickel being electrochemically polarized, where we can produce lots and lots of nickel ions. And what you're going to see is that this is the nickel here, the blue bit. This is the background color. If there's stuff that comes onto it, it gets brighter. So what you'll see is a lot of salt crystals forming outside, and they'll all settle down on the metal surface. So let's see that happen. So here we've got we've got nothing happening. I'm afraid we might have to, oops, oh no, there we are. So here we can see that we've got metal ions going out into the solution, starting to form salt crystals, and then the salt crystals all settling out on the metal surface. So that means that if you've got supersaturation, you can get this salt layer which slows down the rate of electrochemical processes. So then, of course, we wanted to know if these happen within real pits. So therefore, we took the same pit experiment that I showed you about growing the shape of it, but then we kind of jiggled it around a bit so that the beam, the diffraction, we could put a diffraction beam and then corrode the pit through the beam. So if there was a salt layer there, we could see it. And so you can see it sort of grows through it like that. And so whoops. So it's a bit hard to see here. So this is the Bragg diffraction from the stainless steel. And you can see these little speckles coming through. And these little speckles are salt layer forming at the bottom of the pit. And it's a bit hard to see from those little speckles. But if we add them all up, you can see some nice diffraction rings here. Some of them are kind of curved one way, the other ones are side to side. That suggests we've got some anisotropy here. And so what we can conclude from this is that, we were able to index it, and it's ferrous chloride, despite the fact that we've got nickel and chromium in stainless steel as well, but it's ferrous chloride that forms first. And you can see the anisotropy, and that's evidence that we've probably got little flakes of salt settling out on the bottom surface. We had a bit of a play with the crystallography, and that was the best thing we could come up with. So now we've got an idea that we've got pits, and different things are controlling different parts of the pit. So essentially, we've got the salt layer at the bottom, we've got rapid dissolution at the sides, but what's happening further up, well, that's where it's getting more dilute, and that's where we're thinking maybe it's not acidic enough to stop the passive film from forming, so maybe we've got some passivation going along there. So if you think about it, we'd ideally like to know a function which is what the local dissolution rate would be. I is usually the descriptive of current density. So the local rate at each point around the perimeter is going to be controlled by two factors. One is the interfacial potential, and the other one is the solution concentration. And both of those are going to have an effect here. So we've got a rather tricky three-dimensional problem. And three-dimensional graphs are a bit hard to do. But to get our heads around about thinking about it from a thermodynamic standpoint, before we get into the kinetics, corrosion people usually work with what are called Courbet diagrams. So these are thermodynamic maps as to what the thermodynamically stable state is under different conditions of interfacial potential and solution chemistry. In this particular case, we've got the interfacial potential going upwards, and as you might expect, iron is thermodynamically stable at low potentials. You get a bit corrosion high up, and if you go a bit further up, you might end up in the region where you formed a passive film. Here, if you've got a high pH, more alkaline solution, the passive films can become more thermodynamically stable. And so you can see here that if you go up in potential, you can end up in a passive region, and also if you go up in pH, which in effect would mean lowering your concentration of metal ions, you might also end up in a passive region. So what I tried to do here was to represent the three-dimensional map about what's graph of what's going on in 2 dimensions. So what I've done is I've put the interfacial potential going upwards, I've got the metal ion concentration going to the right. Note that acidity is high concentrations. And then, to represent current density, I've used a heat scale with black, meaning nothing happening. So we've got a passive region here with very, very low currents. And here, if we're in the active region, as we go higher and higher and higher in potential, we'll get faster and faster currents. Pretty strange looking shape, but it might be useful to think about. So how might this arise? And this is all very speculative, but I think it's an interesting way to think about what might give rise to these kinds of instabilities. So essentially, we've got a situation where we've got competition between the dissolution process and the oxidation film formation process. And both of these are electrochemical processes, and in both cases, we have a linear relationship between the log of the current density and the interfacial potential. Now let's imagine, for example, that, so I've put a nice line here to represent oxide film growth, but let's suggest, for example, that maybe the dissolution process is kind of similar in location, but with a slightly different slope. You can see here that you've got a region at low potentials where Yes. So we're in a situation here where dissolution wins at low potentials and passivation wins at high potentials. And so if you plot what the current density might look like, you've got the current density going up and up and up as dissolution gets faster and faster and faster, and then passivation switches everything off and you go back to a very low potential. And this works... Oops. Hang on, that's gone too far. Got to go back here. Right. So you can go up this line here. You can see you get faster and faster dissolution, and then it crashes off being passive. And then if you then then if you say maybe if we've got a more acidic solution, we might have a slightly higher dissolution kinetics. And so again, here you might have a higher current density, which then crashes out with passivation at a higher potential, which is like this line up here. And so you can imagine this diagram as being a guide as to how you can get instability inside corrosion pits. And you want to think about this as a critical current density. You can go faster and faster and faster before it crashes. And this is something that is really sensitive to both of these parameters. So can we actually link some of this back to our videos? And you can see here we've got the pit, we can see the perimeter of it, and with some nice image analysis, you can look at successive frames and see how, see how the velocity of the interface, the rate at which it grows, varies in different parts. So you can see at the bottom, the velocity is slow, and at the sides, the velocity gets quite a bit higher. And so we can relate that there. You can, so if you can, so this is the distance along the boundary. So if you imagine working your way around the perimeter of this, and this is the local current density here, you can see that in the middle at the bottom, the current is pretty low, and at these lobes at the side, you can see the current density is quite high, including particularly high here at this rather vigorous lobe. And what do we think is actually happening here? Well, I'm exaggerating the shape here. You can see if you've got the top of the pit and then you've got a bulge where the lobe's starting to come out. If you think about it, you've got a concave region where you might be slightly increasing the concentration of metal ions, which is slightly increasing the acidity, which is favouring this dissolution part, whereas on the concave side of it, you're tending to disperse the metal ions and therefore slightly reducing the acidity. And this may be sufficient to trigger, might be sufficient to trigger a change. And if you can think about it in this framework here, essentially, this is exaggerated here. What we've got is a tipping point. And so the tipping point here is where it's pretty linear, and that's represented by this point here on the line. What happens is that if you're in a concave region, it'll take you into a more active direction, so you'll go in this way, and conversely, if it's convex, you'll go in this direction, so you'll go passive. But actually, it's even worse in pits, because if you're closer to the pit mouth, you have a higher interfacial potential. So that will take you upwards as well as sideways, and that will really reinforce the stability, whereas deeper in the pit, it will go down into the active region. And so you've got this real tipping point that can happen at any point in the particular structure, which is going to give all of this instability. So to finish up, essentially, when people try and carry out electrochemical processes, we quite often get very, very irritating roughness. There's a reason for how it happens, and maybe understanding it can help manage it a little bit more effectively in the way that we carry out experiments. But that is obviously work for another day. So what I'd like to leave you with is another of my videos, which I like a lot, which actually covers a lot of the things that I've talked about in this talk. And that is the potentiodynamic polarization of nickel in hydrochloric acid. And we slowly increase the potential, increase the potential of the metal. And as that happens, you'll see increasing roughness, and then the roughness will actually start to detach, we think, little bits of metal. Then we'll get supersaturation of the solution. Then we'll get a salt layer coming, and you can see what happens. So I hope that this video is going to run. And I'll leave you with it, and thank you for your attention. Right. Let's see if we can... Oh, can you get it going? Yes. You can see the roughness is getting greater and greater, and then the little bits get detached. And you get supersaturation, lots of salt films, and then it all settles down, and the little bits of metal are dancing on top of the electrode. So thank you for your attention.
Okay, thank you for that. Do we have enough time for one quick question? Yep.
You showed the pitting corrosion occurring in an aircraft blade. Now, in T83AL, single crystals are used in aircraft turbine blades. Yes. Single crystals. Will there be titanium is being HCP? Will there be any anisotropy? There should be anisotropic corrosion, right? Do you have any comment on anisotropic corrosion, because titanium is a hexagonal growth factor? And another small question is, MgCl2 is we used NaCl, MgCl so that to accelerate the corrosion. These are my two questions.
So, essentially, turbine blades, that's very much high temperature processes. Those are nickel-based superalloys.
I'm sorry, I can.
With the fuselages that I'm talking about, they're aluminium fuselages that was very much interesting. I'm sorry if I didn't make that clear.
I didn't follow. I don't know.
Sorry,
Okay.
we can't hear you. If you can just move closer to the mic.
Sorry about that. Yes, sorry. Turbine blades, those are nickel-based superalloys, single crystal nickel-based superalloys, and they're very high temperature. So it's a rather different regime there. And the situation I was talking about was the fuselage of aluminium planes. Titanium has different corrosion issues.
Okay. Thank you.
Okay. Yes, if there's any more questions, I'm sure you can catch up afterwards. And up next, we have Robert Elkington from the School of Mechanical Engineering talking about engineering cartilage defect replacements, a soft solution to a hard problem.
Good afternoon, everyone. I'm Rob Elkington, a third-year PhD student in the School of Mechanical Engineering, and very fitting for today, also a Bragg-funded PhD student. So it's really quite exciting to give you a bit of an introduction and sort of a high-level overview of my project, really. So engineering partial joint replacement is a soft solution to a hard problem. You'll see why it's called that very soon. But we're gonna focus on the context of this project: biomimetic cartilage resurfacing. So, cartilage defects. Some of us in this room probably have one. They're present in up to 80% of symptomatic osteoarthritis cases. Are associated with accelerating and increasing rates of cartilage loss. They don't heal. Cartilage is avascular. Once you damage it, particularly if you're older, it's over 40, really, these lesions only really get bigger, disrupt the joint homeostasis. As your body adapts, it might, overload another side, and these things tend to compound. And that eventually leads to quite severe cartilage defect cases, which indicate quite a quick, six-fold increase to the likelihood of having to undergo total joint replacement within 4 years of sort of finding one of these symptomatic lesions. Many of these are also asymptomatic because we can't feel our cartilage, there's no nerves there. So, what happens if you want to avoid total joint replacement and you've identified one of these lesions? These are sort of the 4 broad therapies available on the market right now. So hemiarthroplasty. So that's where you might replace sort of one whole side of the knee with a piece of cobalt chrome. I think some ceramics are used as well. But that's not very good for interfacing with cartilage. A hard material and a soft material, you get a smaller contact area, higher loads. So whilst it's, you can implant it and the patient can probably walk out, it is immediately load bearing. It's not really matched for cartilage, and it certainly doesn't restore natural joint function. Mosaicplasty. So they'll take cartilage from kind of an unloaded area of your knee and transplant it to the lesion. It takes a while to heal, quite painful from what I understand. Yeah, the moduli sort of managed to interface with the cartilage on the other side, but again, doesn't really restore the joint function. If anything, you lose tissue. So a cobalt chrome focal implant, that's where you might take the lesion, just replace it with a smaller implant, a bit like a hemiarthroplasty. So again, it's immediately load-bearing, not really matched for interfacing with cartilage. You still have that hard and soft problem. And then cartilage scaffolds, really. That's kind of probably where the future of joint repair is going to be, but that technology just isn't there. What we have right now is we have scaffolds that take a very long time to heal, and they also regrow biomechanically inferior fibrocartilage instead of the articular cartilage that we need. So maybe they'll match to interface with cartilage, and maybe it'll restore joint function, but again, it's not really quite there. So let's take a bit of a dive into why your joints work so well. So right, the macro scale, your knee as you move. Your joint contact area migrates as you move. Really low coefficient of friction, sort of on the order of 0.01, which sort of means that you're dissipating pretty much all the load that's going through your knee. If we zoom in, we start to understand the biphasic properties of cartilage. So your cartilage is a bit like a sponge. It's about 20% collagen, the rest is water. Most of your joint loads, in fact up to 90% of your joint load is borne on that interstitial fluid pressure. This is a dynamic system. Depending on how you're sort of moving your joint, how you're loading it, the rate of loading, it's constantly, you know, dehydrating, so pushing water out, but also pulling water in to sustain that fluid load support. And it's very minimal load on the collagen. Collagen's not very good at being loaded. And if we zoom right into the contact, what happens where you actually have to dissipate friction? I'm sure we're all aware that there's synovial fluid in our joints. And what happens at the interface of cartilage is you get these big, well, not big, sort of 50 nanometer thick macromolecular films, which are sort of, can be thought of as, well, they are biopolymers that are just very good at holding water. And then as you compress your cartilage, you're keeping it hydrated as it's pushing water into the contact. So that's a mode of sort of, what's called weeping lubrication. And then right at the interface where these sort of macromolecules are interacting, you get a mode of hydration lubrication where to dissipate friction, they sort of swap water ions between each other. So now we can define a design brief. What do we need for a cartilage preserving solution? So a soft biomimetic implant, much like sort of the hemiarthroplasty and the cobalt chrome focal repairs. So that's sort of formatted implant, but we're going to do it with a soft material. That'll have certain specific surface properties optimized for interfacing with cartilage. So we're going to try and minimize stress and strain at the cartilage contact area to, you know, keep our collagen matrix unloaded. We need to support a mode of hydrated, low friction at the interface. And then we also need something that can support the healthy cartilage in the joint that's interfacing this material to rehydrate during sliding. The solution, well, perhaps one solution, polyelectrolyte surfaces. Conceptually, it's quite easy to think about as an uncross-linked hydrogel. That's how I like to think about them. And these are, sort of, well, hydrophilic polymers are just grafted to a substrate, so they're engrafted. They're pretty thin, sort of on the order of microns, and that is you have some polymer backbone, and then on the side chains you have functional groups that, and then for our purposes, these are charged functional groups that tenaciously bind water shells. And then between the chains, because you have all these functional groups on the side chains, when they're in solvent, they sterically repel each other, and you get this conformation where you effectively get chains standing on end. A bit like a polymer brush. I'm hesitant to use that term because I haven't shown that they're polymer brushes, but this is sort of what we think is going on with polyelectrolyte surfaces. Very easy to produce, so we can produce these in a one-step process. We take a monomer, and here we're going to use 3-sulfopropyl metaacrylate potassium salt. We dissolve that in water. Peak as our substrate. When we hit peak with UV light, we initiate a reaction that produces a radical. And then as time goes on, and we irradiate these surfaces in UV, in this solution full of SPMK, we eventually grow this polyelectrolyte film and graft SPMK polymer chains to the peak surface. So that's a grafting 2 process. So to start sort of looking at the material properties, we start simple. Just use FTIR. Is it there? FTIR shows us that it is. And that's that we can see the presence of these hydrophilic anionic sulfonic acid groups, which is sort of indicated there on the graph with that sulfonate group line around sort of 1,000 centimeters on the wavelength. And then, again, fairly simple test, water contact angle, and that's well, starting with a peak substrate, not very hydrophilic, you get a water contact angle of sort of around 80 degrees. Cobalt chrome, that we're going to use as our biomedical control, slightly more wettable, but not great, around sort of 76 degrees. And then SPMK, functionalized peak surfaces, we're really able to reduce that contact angle down and produce quite a hydrophilic functionalized surface. And indicating, you know, that we really increase the surface energy here. And then if we want to sort of explore the conformation of these surfaces, the sort of more functional properties, we've got DivStem, so taken a surface, dehydrated it, put a coating on it, and then etched it with an ion beam to reveal a section. So that shows, for the rest of the work I'm going to show you, we've got samples of peak with about sort of 300 nanometers of a collapsed SPMK film grafted to it. And then in water, or in PBS for that matter, we've got some preliminary AFM that's not shown here that shows these are sort of a couple of microns thick when hydrated. And on the other side, we've got an atomic force microscopy force map. So we've taken a micron colloidal probe, done a load of indentation curves, and that shows us that the moduli at the SPMK surface, hydrated in liquid, so here we're using phosphate buffered saline or water. We're getting sort of moduli on the order of 1 to 10 kilopascal, which is really quite low, considering that the elastic modulus of, say, peak is on the order of 3 gigapascals. So we've got this very soft material on what is quite a hard substrate. So we're going to start to try and test and validate these against cartilage, and we're going to test our theory. Is this a functional material? So there I am harvesting some cartilage off a cow knee. It's not a great job. And then on the bottom, we've got some, so that's femoral condyle, and we've sort of drilled cartilage plugs out of this, about 8 mil in diameter, and these are all flat plugs. So this is the first test setup we use, fairly simple, and that's we have a rigid load cell, and a displacement transducer, and we have a cartilage sample, and then on the lower side of the setup, we have a bath, fix our sample into that, put in a test fluid, so that our SPMK peak can remain hydrated through testing, and then we just slide. We reciprocate the bath back and forth in a linear fashion at 10 millimeters per second. And all of it's sort of in closed loop control, so throughout sliding, we're maintaining a 30 Newton force, which is roughly 0.75 megapascals in this geometry, which is on the lower end of the kind of forces our joints experience. So what are we actually looking for doing these tests? Is there a laser pointer? Am I a good engineer? Have you turned it on? There we go. So, unloaded cartilage. You've got a load of collagen, chondrocytes here, and when it's unloaded, it's sort of in just a state where it's basically just a hydrated network. In a healthy loading pattern, what happens? You compress the collagen network, which is fine, and then you get this interstitial fluid, which supports most of the joint load and protects all this delicate collagen, all this carefully aligned collagen in our cartilage. And we can also see around the edges, as we compress it, it weeps out fluid, which is a good thing. That hydrates our contacts. When we abnormally load it, or what happens when you have, compromised cartilage, you've torn the collagen. So this sort of pressurized state breaks down, the cartilage is damaged, much weaker, and it's unable to kind of be in this state where liquid is actually supporting the load. You get compounding damage in the cartilage. So to that end, to analyze it with our test, we're going to sort of look at a couple of very basic loading parameters to understand what's happening with the cartilage, and that's the friction coefficient. So that's just the ratio of the shear force in sliding, and then the tangential force, so the load, 30 newtons. And then the strain, which is a ratio of how compressed the cartilage is compared to its normal height. So again, we want to minimize this. And then this equation on the other side is it was validated in the 80s. It's quite a simple model. It can be thought of as just a one-phase exponential decay. So exponent term there and some time constant. And then a load of other parameters to make it fit for cartilage. Suitable stress, that's some aggregate modulus. And that's quite a simple way of understanding the rate, the time-dependent properties of this cartilage strain and how it's loaded in time. And that will become more important in a moment. So, start simple. We've slid it against our peak material, some cobalt chrome as a biomedical control, and our functionalized material for 2.5 hours. Peak, what happens? Well, friction increases over time, and we get quite a high friction coefficient. That's a bit of a problem. It means we're probably damaging the collagen matrix. It also shows us, or rather implies, that sort of weeping lubrication, water coming out of the contact, has stopped. Friction has kept increasing, and then it's reached some point where this is indicative of solid on solid friction. Cobalt chrome, slightly better, perhaps because it is slightly more wettable and able to maintain more liquid at the interface, and thus provides a lower friction interface for sliding. It's still not brilliant. Friction coefficient of 0.35. And then for our functionalized surface, well, over the whole course of the test, we're able to maintain really quite a low friction coefficient, which is on par with what you'd expect for, healthy cartilage on cartilage contact. So where it gets more interesting, and where we begin to understand what's happening a bit more, is by understanding the strain. So this is our benchmark. We're not sliding in this test. All we're doing is we're taking some cartilage and we're compressing it for 2.5 hours to understand its behavior. How does fluid leak out? So initially, you get rapid fluid exudation, and then you get the exponential decay of fluid. So that's our decay, exponential decay model that we just evidence that we just discussed. So you get an exponential decay until you reach some equilibrium deformation, where like the fluid phase is able to support whatever the remaining load is, and then that's also shared with the collagen phase. So we're looking to minimize this, really. Minimize both the strain and the time it takes to reach that equilibrium deformation. So no sliding, we're getting about 50% strain in cartilage when loading it in this test setup. So when loading and sliding against peak, again, we're getting a very similar pattern of behavior. So that initial rapid exudation, that's okay. And then it continues, but it kind of overshoots here. But what this does show is in sliding, there is absolutely no evidence of rehydration. Water is not working its way back into the collagen matrix. It is pretty much analogous to what you'd expect if you just compress cartilage. Again, very similar time constant to reach this quite high equilibrium strain. And another sort of feature of this graph is that the strain actually continues increasing. It doesn't really reach an equilibrium. I'll mention a bit more about that in a moment. Cobalt chrome, again, slightly better material for this because it is slightly more wettable. Same profile of behavior, quite high strain again, 40%, and again, sort of a similar equilibrium time constant to reach some kind of strain equilibrium. And then our SPMK material, well, that's really quite interesting because what we're able to do there is much quicker reach this plateau where there is, well, first of all, it really reaches equilibrium much quicker, probably sort of almost 2/5 of the time of the other samples, but also a much lower strain. Now, what that lower strain tells us is that we've reached some kind of equilibrium state that through sliding, whilst, we're loading it, fluid's coming out, but we're also able to get fluid back into that cartilage and reach a much lower equilibrium strain, thus shielding that quite delicate collagen matrix. And we can visually validate that too. So this is an FBI grade transfer material. So we've taken our cartilage plug after testing, and we've put this transfer material on and we looked at it under a microscope. So when sliding against untreated peak, we see these really quite big tears in the collagen matrix. So that, that's in line with the theory we just discussed where, high friction, high strain, we're going to damage the collagen matrix. SPMK peak, absolutely no damage. And that makes sense. We maintain low friction and a low strain. It is incredibly likely that fluid pressure, that fluid equilibrium, so that flow of fluid is occurring. And that's a healthy mode of sliding against cartilage. So I suppose what I've just told you is sort of an indirect analysis. So let's sort of zoom in a bit more. So obviously we don't spend all day walking around sliding. We stand up, we sit, move around, do whatever else. So we're going to develop our test a bit further. And that is 30 minutes of standing, so that's just compression really, and then 30 minutes of walking, so that's sort of sliding, reciprocating back and forth at 10 mil per second. So again, let's look at the friction and the strain response. So peak, static loading, no friction there. And then as we start to slide, because we've already exuded quite a lot of the fluid out of contact, we're starting with quite a high friction coefficient, and it just keeps increasing. And again, in the second phase of sliding, friction drops slightly, so I guess we're kind of working fluid back into the contact interface there. But again, we're getting a really quite a high friction coefficient. SPMK peak, when sliding, in a stop-start regime, at the start of sliding, we're able to recover back to that really low friction coefficient, which is really interesting. But this is even more interesting. So static loading, again, we're continuing the load here. So throughout all these cycles, it's loaded for 30 newtons. Let's look at the peak response in red first. So over this whole test, through loading, sliding, there's absolutely no evidence of kind of that strain recovery, of liquid moving back into the cartilage. The strain just keeps increasing, cartilage keeps compressing. But with our SPMK peak material, as we load it and then start sliding it, we're actually able to recover some of that strain. So that's a direct measurement there, showing that this SPMK peak material is able to work fluid back into the cartilage and really support that mode of biphasic lubrication. And again, shield the collagen matrix from damage, which makes it quite a good candidate material for acting like cartilage. So a quick summary of sort of SPMK peak and what we've shown so far is that we're able to sustain really quite a lubricious interface. Friction's always been low against SPMK peak, and we're able to minimize shear forces at the cartilage interface and keep that collagen matrix relatively unloaded. We've also got evidence now that it supports the kind of that biphasic fluid load support. So it minimizes the cartilage strain, and it's also able to induce cartilage rehydration in dynamic conditions. Say you're standing up, you're pushing fluid out of your cartilage. That's unsustainable. So when you walk, you're pushing fluid back into your cartilage. And we're able to do this with this material. And again, throughout all the tests, we've noticed no damage to interfacing cartilage when sliding against SPMK peak. So the kind of broad conclusion here is that polyelectrolyte surfaces are able to support natural joint function and enable preservation of healthy cartilage. So I guess for those of you that are switched on right now, what we'll do with the sound thing, that's not an issue. I haven't actually shown you a direct validation of what it looks like compared to cartilage on cartilage data. That's because cartilage is a very uneven surface. In the test setup we've been working with so far, the PID, that closed-loop control, wasn't good enough. We weren't able to move on, basically taking the condyle sample from that bovine knee. It's curved. We can't move the contact and maintain the load of what we've shown so far. So we're having to develop some new hardware. This is a tribometer, very similar to the one I've shown you, but what it's now enabled with is something called fuzzy logic, which is sort of more of a open loop control. It's able to respond to the changing in mechanics very quickly and hopefully move over uneven surfaces to provide direct validation to cartilage on cartilage contacts. So cartilage on cartilage versus cartilage SPMK to really hammer home, if these materials are candidates for actually behaving like cartilage. And then we can also put through real gait loads. When you're walking, load isn't constant. Load goes up, down, as you have heel stroke. And then on the other side of that, we're going to develop some sort of concept implants. We're going to, take a knee and actually articulate it. So this is a setup that I developed last year with a master's, very good master's group, to retrofit onto one of the joint simulators available in engineering. And that, bit of a work in progress. I've got a year left of my PhD, so it's probably what I'm going to be focusing on. And that's taking like an actual peak implant, somewhat reminiscent of a hemicap, functionalizing it with my material, and demonstrating directly in a bovine knee. With preclinical loading patterns. So I hope that was somewhat interesting. Thanks to the team. It's Professor Michael Bryant, who's somewhere in here, Dr. Rob Beelan, Professor Richard Hall, our surgeon, Professor Hanan Pandit, and then, most of these experiments wouldn't have been possible without the support of my peers, Greg and Nick. So thanks for listening, and follow me on Twitter.
Yeah, thank you. Okay, we don't have any time for questions after that, so I'd like to again thank our speakers from Functional Surfaces.
Okay, and I think with that we'll jump straight into our next session, which is multiscale materials. And I'd like to introduce Professor Robert Kay, who's stood right behind me. Take it away, Rob.
Good afternoon, everybody. I'm here to talk to you about hybrid additive manufacturing of functional materials. And so I moved into the sort of 3D printing additive manufacturing arena about 10, 11 years ago, when it was really hyped up. The press were saying it's the future of the world. And I was quickly very disappointed. You couldn't make any functional products. You couldn't make a watch, your glasses, your smartphone. There was lots of trade-offs, in particular material limitations and resolution limitations. So I've spent the past sort of 10, 11 years trying to develop these processes and actually get them to work to make things like electronics. So today what I'm going to talk to you about is what's called hybrid additive manufacturing. And what that means in a nutshell is it's a combination of different digitally driven techniques. So it could be multiple 3D printing processes in one platform, or it could be additive and subtractive. But the whole point is that it's computer control. You're not having to use templates and tooling, so each product could be different. And I'm going to focus on two particular examples where the importance of the material innovation and the process innovation coming together are really important. So one's 3D printed polymer electronics, and the other one is technical or engineered ceramics. So just to start off with, if you take something like 3D printed electronics and you compare them to mass consumer manufactured electronics, it's like going back to the 1960s. So you cannot make high performance goods. And so something really needs to change here. Looking at a full electronic system, what you have is a circuit board. And so that's your electrical routing. And typically I use the analogy, that's kind of like your road network. So that allows all the different components to communicate. Then you'll have integrated circuits. So they're typically made from a semiconductor material, and these will be things like your microprocessors, your memory. So kind of the brains of the system. Then you have other things like discrete devices, such as passive components, things like resistors and capacitors. And then modern devices like your smartphone, you have sensors and actuators, like the display or the camera. And then finally, that's all brought together mechanically and electrically through the assembly and packaging. And I think that in terms of additive manufacturing, 3D printing, pretty much you could do all the ones in green. I don't really see the point of competing with the integrated circuit because you can use those as your building blocks that will allow you to make any combination of electronic system. So I started out in earnest about 2013 on a project between 4 universities, and we were trying to use existing 3D printing techniques. So we used things like stereolithography and dispensing of silver paste. And yes, we were able to make a 3D multi-layer electronic device, and we made a very simple demonstrator, a 555 timer with a little flashing LED. But the problem was that we couldn't make anything high performance. They had a tendency to fail. If one of them we dropped off the bench and it instantly stopped working. So it wasn't going to be the future, in my opinion. So where do these challenges come from? Well, if you look at the materials such as paste and inks, they're commonly dispensed or inkjet printed. They don't like to stick to the dielectric beneath it. You don't get the same material properties as, say, bulk copper. And then you've got this whole issue around scaling. So it's not very easy to print paste and inks at very fine resolution. And it's not just the transistors and things that have shrunk, but it's also the whole overall system, the packaging that goes along with that. So you need to make very small interconnects. So what we decided to do was I teamed up with a team up at Heriot-Watt that did a lot of material science work, and at the time they were taking Kapton tape, polyimide film, and they were chemically modifying that, and they were able to make flexible electronics. And so I was wondering, is there a material in 3D printing that we could do the same thing to? So what we found was it was a material under the trade name called Ultem, and what that actually contained was polyetherimide, so it had that same functional imide group. So you have to print this at quite a high temperature, about 365 degrees, so it's not like your common 3D printed filaments that you print about 200 degrees, but that wasn't too hard to overcome that issue. And the next thing that we do is we dip the printed substrate into potassium hydroxide, and what that does is it actually cleaves the imide ring and creates it leaves a potassium ion within that functional imide group. And then we would dip this into another beaker of silver nitrate solution, and that would create an ion exchange. So suddenly we had silver ions embedded within this part. So here you can see the fused filament printing process. This is fused filament fabrications, the common desktop printers that you get, in home hobbyists and educational places. But this polyetherimade's got some great properties in terms of its dielectric, thermal properties, chemical resistance, biocompatibility. So then, as I described, we do this chemical modification stage where we take that functional imide structure and we put the potassium hydroxide in, and then we do the ion exchange. What that allows us to do then is shine UV light onto the surface of that, and that selectively reduces those silver ions down to silver nanoparticles. In this case, because we want a digitally driven process, we used a laser rather than, say, a photomask. These silver ions then act as a seed site so that you can electrolyse grow copper. So again, this is simple lab work, so it's done in a beaker. But suddenly we've grown bulk copper, the same that's used in the printed circuit board industry. We then dispense solder paste, because again, we want this to be a digital process, so we don't want to use any templates like stencil printing, and then we'd pick and place the components. And then finally, we reflow the parts using a standard solder reflow process. Okay, so I'm just going to show a few examples of how we validated this as a technique and why we think this is quite an important way of analyzing and developing a 3D printing process instead of the sort of traditional methods of paste and inks. So the first thing we did was we just took the filament that you get before you put it into the 3D printer, and just did these beaker tests, because you're never sure with 3D printable polymers what they've been modified by, things like plasticizers and things that might just stop this actually being able to work. But we were really pleased to see that occur, and we just had that on a 1.75 millimeter diameter filament. The next question was, well, this isn't printing paste, so is this going to actually bridge across the individual printed layers, or are we going to have open circuits? And we're really pleased to measure the continuity across that. And when we did the 4-point probe measurements, we found that it had very good conductivity, about 2/3 the value of bulk copper that you'd find in a handbook. So that's very similar to electrolytic copper deposited today. Now, the other thing is people have probably used things like Kapton tape know that it's very flexible. It's used in flexible electronics. Polyetheramide has very similar mechanical properties. So normally, if you print very thin layers of 3D printed polymers, they have a tendency to very easily fatigue and tear and break. But we also wanted to test this from a point of view of, is a copper ductile enough? Is it reliable? You know, we're trying to, we believe we now have a chemical adhesion rather than just a kind of a printed mechanical adhesion here. So we're quite delighted to see that by printing 2 45 micron layers, so a part that was about 90 microns thick, so the same thickness as human hair, was very, very flexible. So the next thing that we did was, oh, the video's not playing. It doesn't matter. So what we did was we made parts that had rigid sections in the end, and then they had flexible sections within the center, and we had a long meandering copper track. And we built just a bespoke bend test rig that would just constantly pull the part and then bring it together and create that bend radius. And we did 6 samples, and we ran each sample for 50,000 cycles. So the first thing was, it was great every morning we'd come in the lab and see that it was still working. So it showed that reliability, the adhesion, but also we're really pleased to see that these parts had very minimal drift and resistance. It was only about 1% after 50,000 cycles. Something that we haven't really managed to play around with, but maybe a bit of thought process, is normally when you take electronics, they're typically made of different systems that are assembled together, so they kind of plug in. If you're able to print both rigid and flexible areas, is it possible to minimize assembly? That's not always the best thing in terms of yield of products, but it's still a new design freedom potentially. The other thing that we wanted to look at was, if you've got something that bends, then as you bend it, the resistance changes. So we were looking at positional sensors for this technology. And then we collaborated with electrical engineering to look at wireless communications. So one of the things about being able to have a 3D printing process is you're able to make conformal antennas. So the team in electrical engineering designed a flat antenna and one on what we simulated as a small pill capsule, basically. And we fabricated those and then handed them back for them to test. They tested it between 0.1 up to 10 gigahertz. So that was to cover Wi-Fi, mobile phone frequencies, and the industrial, scientific, and medical band frequencies. And we're very pleased that there was a very good agreement between what was simulated and what we actually measured, both for the planar and for the conformal antenna. I think it's important to highlight that with 3D printing, when you get these filaments, the data sheets only go up to 1 kilohertz. So there's quite a challenge on that, and both the conductor and the dielectric properties are really important. The next thing we wanted to look at was wireless charging. This was more because in modern electronics on the circuit board, that you typically have vias, which allow you to make multi-layer, high-density boards. And so we wanted to see if we could get this process working to create a through hole. And in this case, because it's a planar coil, you need 2 of those, but on each coil you need a return pass, so you can't have that copper track going back across the spiral. So we were very pleased to see that we were able to get the air, fuel, and the RFID standard, but with the one that we made, we had too much return loss to hit the key standard. However, more recently, we fabricated one that has a much higher turn ratio, which should overcome that issue, basically. The next thing we wanted to look at was people were not using solder on 3D printed electronics, so they're still using paste and inks, and that's where I think the reliability issue comes from. Solder creates that metallurgical bond, and so it creates a very reliable interconnect. So initially we just tested a simple 555 timer like I showed you before, and it worked, and we're very pleased. So more recently what we did was we actually looked at a range of different common commercial components, everything from memory chips, microprocessors, to sensors like IMUs and passive devices. And we've been using a Type 5 tin silver copper paste because that's the most common lead-free solder paste that's used by the consumer market. And then lastly, we were quite interested in embedding a shape memory alloy into these parts. So we could use, in this case, we're using nitinol. And what happens is when you heat nitinol to about 50 degrees, it goes back to its original position. So in this case, what we did, instead of what they normally do with nitinol, is they dual heat it. So that's when you actually apply the charge to both ends of the part, and that causes it to heat up, so that resistive dual heating. But in this case, what we did was we used the copper traces to make selective regions for heating. So that meant we could selectively actuate that nitinol also. So what I'm interested in on this is basically if you can incorporate movement into 3D printed structures, you can make foldable and deployable electronics. So maybe something where, maybe in a satellite application, or maybe something if you post it through somebody's mailbox and the thing opens up. I believe these videos on the bottom aren't working, but what you can see is that from the 3 different heating zones, we could create 8 different states of the movement. If anybody's interested in this aspect, we published the kind of material science work in Advanced Functional Materials, and then the process development and the demonstrators in the Journal of Additive Manufacturing. Okay. My other example I wanted to cover today was on additive manufacturing of ceramics. Now, if anybody looks at 3D printing ceramics, what they found is that people have taken metal and polymer processes and they've adapted them to print ceramics. And what that's done is it's created a lot of trade-offs for most industries. So there's certain materials you can't process. You quite often have to change your feedstock formulations. Quite often there's higher issues around things like higher porosity, higher shrinkages. And ceramics are quite a wonder material, really, because they've got really high hardness, they're very chemically inert, great thermal properties, high resistance to things like heat, corrosion, and wear, and they can be biocompatible materials. So that's why they're used in so many different industries. So what we thought about was, is it possible to use a hybrid technique of both additive and subtractive? Because with material extrusion of heavily loaded ceramic paste, you can print them, but you don't generally get a very good resolution. You have stair-stepping and other issues like that. So what we do is we print the ceramic paste, and then we would do some machining operations that would level the part, or it would take the near-net shape and be able to do contouring to make sure it was at the feature size that you expected. We also integrated in this particular platform the ability to print sacrificial polymer. So if you wanted to say overhangs, or you wanted some sort of channels or something like that, you could get those features built in. And then also on top of that, we integrated within the platform infrared drying, because this is an aqueous paste, so you want to speed that process up. One of the PhD students, Dan Davey, he's actually looking at this because from a printability, a rheology kind of point of view, printing ceramics is quite challenging. You've got a lot of different types of ceramics. They've got different sort of powder morphology, powder size distribution, and so that then impacts how you actually formulate these ceramic pastes. And the main thing is that you want the material to be able to shear thin, so it flows out the nozzle, but then once it's deposited, it doesn't slump, it retains its shape. So it's that printability. And so Dan's currently looking at all these different parameters across about 10 different ceramics and trying to develop a kind of handbook on how you might be able to formulate a wide range of ceramic pastes. So the advantages of a hybrid additive manufacturing process for ceramics, I think, is that you can use these conventional materials that industry are already using. So in theory, you could put one of these into a production line and not change the front end processing or the back end firing. You can produce a range of different 3D geometries using these materials, and to date, we've tested Morgan Advanced Materials commercial material, and we got the same density, 99.93% as our production materials, and we got the same shrinkage rates as what they'd get in production, which is about 18%. Also, what we've done, which is something I think that makes us quite unique at Leeds, is that we took that lab concept, did some of the material development, we then built a platform in our lab, but then we actually built a system that's now in industry. It's in an R&D lab in one of our industrial partners. We produced this system, we designed it and manufactured it, and it is CE marked. So I think that's quite a unique thing, because now we can co-develop with that company and they're using it to develop their next generation of products. I think in the thing of time, I'll just skip this video. Okay, just one last thing to quickly show you. If you have a hybrid process where you can do something additively and subtractively, we have a PhD student, Lewis Masters, who's currently looking at, can you do defect-free manufacture? So never scrap a part that comes off your machine. So what he's looking at doing is implementing things like laser scanning and a camera, and then getting the system to say, is there a defect there? And if the machine spots this defect, tell the machine to rework just that one layer. So you get the advantages of potentially you won't be scrapping parts, because even in additive manufacturing, if you have a defect in that part, it just typically propagates through. But also companies could qualify high value parts too. Okay, so just in conclusion, I think hybrid additive manufacturing has a real potential to overcome the limitations of standalone 3D printing processes. I think you need to consider both the material science and the advanced manufacturing processes concurrently. You don't modify an existing process, you work on them together. And I think that's what's going to really enable next generation products. I'm a big believer that success in research is achieved through multidisciplinary collaborations. That's why the Bragg Centre is great for this, but also involving other academic institutions, industrial partners, and research trade organizations. So hopefully this will help me connect with this research community. And just thanks to our sponsors, academic collaborators, industrial partners, and here are my contact details if anybody wants to reach out. Thank you.
Thank you very much. Some incredible work there. Do we have a few quick questions? And if not, we can take them to the break after the next speaker. Jerry.
Do you want to comment on something that you didn't really touch on, which was speed, process speed, and how that is impacted, particularly in the electronics areas?
Yeah, I wouldn't say that this is a high volume manufacturing process, especially for electronics, but what it would allow you to do is to rapidly produce a 3D circuit electronic system and test that concept, or make something that's bespoke, maybe patient specific, user specific. But yeah, you're right, I wouldn't see this at this stage as mass production, definitely. Yes, in some ways you could think about it that way, because for example, the patterning stage, we used a laser, but in theory you could use something like a DLP, which moves from a parallel to a sequential to a parallel process. There are some challenges around that though, because you're now working on a 3D topography, so you get that projection. But yeah, potentially.
So one other quick question. In which case then I think we'll thank our speaker.
Great. Thank you.
And I'll invite Dylan down.
Hi, my name is Dylan Barker, and I'm a third-year PhD student in the School of Physics and Astronomy. And I'm going to talk to you about my attempts to automate scanning probe microscopy, some methods in that using machine learning and some other stuff. So firstly, a quick outline of what I'm going to talk about. So I'll introduce scanning tunneling microscopy, which is the main method of microscopy that I use. I'll go through machine learning and some other deterministic approaches that I use for image classification, and then I'll run through some results in comparison between some other stuff. So firstly, what is scanning tunneling microscopy, or STM? The idea behind it is we have this atomically sharp probe tip, so this is tip in green, at a surface. And when we bring the tip close to the surface, electrons are able to transfer across the junction. And if we measure this flow of electrons, we can measure a current. And this current is exponentially dependent on the tip sample distance. And what that essentially means is that all of the current you're measuring is coming from the very apex of the tip. So the tip shape is very important when you're running STM. So in the main method of STM that I use for imaging, which is constant current mode, what we do is we aim to keep the current constant while scanning over a surface by varying that tip sample distance. And if we do this while scanning, we can build up a contour of how the tip has to move. And then if we extrapolate this into 2 dimensions, we can build up some nice topographical images. So when we're working the scale, we want to image single atoms and molecules. We need everything to be as clean as possible. So we work under ultra-high vacuum conditions. So in atmosphere, all of your surfaces will be covered in a couple of layers of water, oxygen, other contaminants like that. So we heat them up, put them in our UHV chamber, and they should stay clean for long enough for us to image. So I'll quickly run through a couple of the surfaces that I'll be showing you today. So the first one is silicon 111. So all of these bright blobs that you can see are individual silicon atoms. And the second one is another silicon-based surface. But these sort of slightly darker blobs you can see are the silicon atoms, again here. So I've shown you how STM works, roughly. But, you know, what kind of stuff can we do with it? So here's just a quick video showing a manipulation event. So moving some atoms and molecules around on a surface. This one's just for fun, just to write COCU. But there's other stuff we can do. We can build very specific structures for our experiments. So as I said, the specific shape of the tip is very important. So when we're scanning and we get an image like that looks like this one, which is quite a good image, we're assuming that our tip is very atomically sharp, so terminate at the end with a single atom. It's not always the case, unfortunately. So when you're scanning, stuff could fall off the tip, jump onto the tip, and cause that tip to be misshapen, and you get lots of different images that look like this. So just for reference, all of these images are of the exact same area, just with different tips. So this isn't the end of the world. If this happens to us while scanning, we can repair the tip in situ via manual indentations of the tip into the surface. And again, what we're hoping to do here is just pick up some material, drop off some material, and just sharpen that tip again. I showed it here happening in a single step. It's a really slow process of us doing this over and over in the lab, checking the images in between, and it can take us hours of this before we can get a good tip. So it's an ideal candidate for us to actually automate. That's what I'll be talking about mainly today. So the kind of crux of this automation script, the thing that we'd need for it would be some kind of way of classifying our images between good and bad. So it's easy if I show you these images on the left and say that's good. You can say all of these on the right are awful. But we need an automated way of doing this. And the main method that most people go to is machine learning. So self-driving cars, handwriting recognition, facial recognition, all examples that everyone's seen before. And they're all examples of what's called supervised machine learning. So the idea behind supervised machine learning is that we have these quite large labeled data sets. So for our toy example, images of Tom and Jerry. And what you do is you input them into your model for training. So I do most of my computational stuff in Python, so I use a framework called TensorFlow, but there's lots of other ways you can do it. And essentially, when you're training your model, what you're hoping for is to output a function where the input will be an image, so Tom or Jerry, and the output will be some prediction of what that image is. And what your model will do whilst training is look at your data set over and over, changing small parameters inside the function, hoping to increase the accuracy of the prediction in the end. So once you've finished training, you have your model, you can input some test data, so just some data it hasn't seen before, and you hopefully can get some nice predictions out of it. So what are the kind of pros and cons of using machine learning? So firstly, on the pro side, it's very widely used, very good at identifying complex patterns in data, because that's what it's built for, and the kind of obvious one of no human intervention. So it does this all by itself. On the downside, the biggest bottleneck that most people run into is just the amount of data you actually need to do this. So you need really large data sets, and you need it all to be labeled as well, which is just a horrible process, basically. It's also quite hard to interpret your results. So if stuff's going a little bit badly in your model, it's quite hard to see why it's doing that. It's also very heavy on time and resources as well. So I'll go through a couple of previous examples of this kind of image classification stuff in use in SPM. The first one here is, on the left, is from the Wolco group. And essentially what they're trying to do is classify these, so a single STM image like this with either a good or a bad tip. So I don't know if you can see very well, but in these small squares, you've got these small defects, which are just bright spots. With a good tip, they'll appear as just a sphere, basically. With a bad tip, it could be anything else. It could be slightly misshapen, two spheres, something like that. So they use machine learning to just classify this binary classification for good or bad. And then there's another example here from the Moriarty group, which is a group from Nottingham, where rather than this simple good or bad classification, they're running with a couple of different, they're trying to classify between a couple of different tip states. So different shapes the tip can be in, where you might get different desirable imaging modes, basically. So they both get quite good accuracies, but the main point here is that they were able to do this because they have quite a large catalogue of images from their previous experiments. And all they had to do was go through, label everything up, and input them into machine learning. So it's not something that every group is able to do. So our workaround for this was building this data generation script. So the idea behind it, start off with a good tip, and you scan over an area, and you output an image that looks like this one. Then what we do is we can move our tip away from the imaging area, indent the tip into the surface, again, similar to how we prepare our tip. But here, we're not hoping to kind of make it sharp, just change the apex in any way. Come back over, after the animation, come back over, and scan again. And we repeat this process of preparing the tip, scanning the same area over and over until we've got quite a large catalogue of images. And then we can go into labeling. So using this process, for the two surfaces I showed you earlier, we got over 1,000 images for each. We then got about 4 people from our group to label all of the images, collect them all together and see how much we agree on everything, basically. And anything we don't agree on, we can throw away, because we don't want to include any of the ambiguity of this like bad labeling into any of our classification networks. So I've talked entirely so far about classification of these images using machine learning. But in other deterministic imaging methods, like optical microscopy and electron microscopy, there are well-established image analysis methods which you can use to determine how good your image is. So the two standout methods here are, first one, Fourier ring correlation, which is essentially a method of predicting the spatial resolution of an image using Fourier transforms. And the second one, which I'll talk a bit more about on the next slide, is called cross correlation. But the idea behind them is to use prior knowledge of the system you're actually scanning to assess how good the images are. So cross-correlation, how does it actually work? So we start off with what we call our reference image. And it's simply a small repeating section of any good image that we've taken before. So for here, on the silicon 111 surface that I showed you earlier, I use just a small section of a unit cell. So then we take our input image, and we scan our reference image over the input image. And at each point, it's measuring how highly correlated the reference image, the small image is, with that section underneath it in the reference image. And I'll output a number between 0 and 1. So 0 being no correlation, it's a very different image. 1 being very high correlation. And then we get this cross-correlation map on the right. So you can see all the peaks here. And if we take, say, the top 20 of these peaks, map them over to our input image and take them out, we can see it's doing what we're expecting, and it's pulling out all of these unit cells from here. So then if we take the average of the actual number that's output by this, we get an average of how highly correlated the input image is with our reference image. And yeah, so we get an actual metric for how good the correlation is there. So how do we use this method to actually determine how good our tips are? So here's just a scatter plot showing the cross-correlation value on the x-axis and the Fourier ring correlation resolution on the y-axis. And then in green, we've got our good images, and in red, we've got our bad images. And so you can see this grouping of the good images on the right-hand side. So what we can do is we can simply just find a threshold. We can say that when the cross-correlation is above a certain value, that our images are good, and below, they're all bad. The Fourier ring correlation is on here, but we don't use this anymore. And the reason behind that is you can get certain images where the spatial resolution is quite good, certain tip states that is, where the spatial resolution is quite good, so it's not too blurry, but it is a bad tip. It's just how STM works, unfortunately. But yeah, we use entirely this cross-correlation method at the minute. So then I'll talk about some results. Now we've got our two methods of classifying our images. But firstly, I'll go through some useful metrics to actually describe them. The first one is the kind of easy one that everyone knows, it's just the accuracy, which is the percentage of the time that our classifier is predicting something and is correct in that prediction. And the second one, which we're more interested in, is what we're calling the true positive precision. And that is essentially the percentage of the time that our model predicts something to be a good image and it's correct in that prediction. So this doesn't take into account any images that are good but are predicted as bad. So we don't mind if it throws away some good images as long as it's very certain when it actually finally gets there that it's a good image. And that's just so that we're not doing any experiments, say, on like using a bad tip. So into the actual results. So firstly, with the Silicon 111 7x7, with the deterministic classifier, so that's using the cross-correlation, we get an overall accuracy of 85% and a true positive precision of 96%. And using the machine learning classifier, we get an overall accuracy of 96% and a precision of 92%. So you can see fairly comparable results here. But the main things to note are the higher precision in the deterministic classifier, which basically means, as I said, it's more sure of itself when it finally gets to a good image, and a slightly higher accuracy as well in the machine learning classifier. So we tried this again on the other surface, the boron-terminated silicon, and we get very similar results with the higher precision in deterministic and higher accuracy in machine learning as well. So, and just for a quick comparison, I've got up here just an average of those other two papers, how their classifier stuff works. So they were using, as I said, entirely machine learning, and they get kind of very comparable results to us. So how do the two approaches actually compare? Firstly, for the deterministic approach. As I said, you get this higher precision, which means there's much less chance of these false positives, so it's more sure of itself. And it also requires much fewer data. So as I said, with machine learning, you require these really large data sets to actually get these image classification things working. With this, you just require that single image, the reference image, to start with, and you can get it going from there. It's also much easier to tune. So you can tune this precision as much as you want just by changing this threshold in the cross-correlation. And you can increase the precision by lowering the accuracy and vice versa. So it's completely up to you how you do it. On the machine learning side, as I say, you get higher accuracy, which means that fewer of these images are ignored, but it does mean it's less precise as well. And it's slightly faster computationally. So as I said, when you're training your model, the final output is just a simple function, so it's very quick actually making a classification. And I'll just show you it working. So here are two videos of, they start off with a bad tip, as you can see, they're quite bad looking images. And essentially what we're doing here is we're running our classifier on each image, and we're crashing the tip in between, and it's just repeating this process of taking an image, classifying it, crashing the tip until it gets a good image. So see this, it runs through a bunch of bad images before it finally, hopefully gets there. Yep. And the same here. And they both, I think, took about 30 tip indentation attempts before they get there, which is about 45 minutes. Obviously, it could take longer. It's quite a random process, but it's much better than us sitting there doing it manually. And just to conclude, so we've got the results in the minute are showing that we've got viable alternatives to using machine learning in these SPM classification tasks, and the methods are showing comparable accuracy and precision to each other and also to stuff done in the literature. And these deterministic methods are using the cross-correlation. It's also quite good because it requires just much less data in that single image. In terms of what I'd want to do in the future as well, so now we've got this automatic tip prep tool. We want to run some fully automated experiments, so some full patterning, manipulation experiments, stuff like that, without having to kind of babysit the program as it goes. And also attempt to build a general machine learning based classifier. And what I mean by that is all of the machine learning stuff that I showed you here, the whole data sets we're using single surfaces, but what we want to do is pool all of our data sets together and see if we can get a machine learning classifier to identify what generally makes a good tip, and see if we can give it a new surface it hasn't seen before and see if it can do well, essentially. And just want to say thanks to a bunch of people. So Adam, Susan, Phil Blowy for experiments, Tim, Jack and Simon for all their feedback, and George and Alex for discussions as well.
Thank you, Dylan. Looking at time, have we got any quick questions for Dylan?
You sort of skipped over about why the Fourier transform method you weren't employing. Is it just not, doesn't seem to work?
So it is just the fact that there's very little correlation in the y-axis here. Essentially what happens is you can get certain tip states where, say, you have two apexes that both, so you get what's called a double tip, which means that the structure looks very different, but it's not necessarily blurry. And that means that you can get, yeah, these ones down here where they're bad images because they look like this, but the spatial resolution is estimated to be quite good anyway.
Thanks.
Are there any other questions? Oh, thank you.
Thanks for a great talk. So I've got two dead quick questions, I hope. First of all, I don't think you mentioned what the tip material is. Is it just a standard tungsten?
Yes, it is, yeah.
Yeah. And there were a few points where you said it was important to go back and scan the same area many times. How do you always sort of guarantee it is the same area?
So we have a script that we built that uses, again, cross-correlation to measure the drift between two images, and then it will compensate for that by moving the piezo's back to that area and countering that in the controller as well. So countering that by, calculate the drift over that time and stuff like that. So
Thanks, that's great.
Okay, I think one last quick question, and then go for some coffee.
So, I mean, it's nice it works most of the time. I'm just interested, when does it fail and why does it fail? Because it thinks it's found a really good image. Why would that be a failure then?
It's hard to say. So sometimes when it fails, so what you'll see in some of these images, trying to think how to word it. So this image is quite a good image, but it's not brilliant. And a lot of it, when it comes down to us labeling stuff, is down to our opinion of what's a good image or a bad image. So I would say that's good, but say my supervisor would say that's rubbish, go back and do it again. So yeah, a lot of the time it does come back to that. It comes back to as well when we use the cross-correlation, what we use for our reference image and stuff like that. But
so it's how you can prove to your supervisor that you're right.
Exactly, yeah.
Okay, well, with that, I think, will you join me with excuse me, time for coffee. With that, can you join me in thanking all of our speakers from these sessions, and then we'll head for coffee. So it's back down into the foyer for some coffee, and I think we're still about 20 minutes late overall, so joining back up again in about 25 minutes time, please. Okay, everyone, if we'd like to take seats for the final session. Thank you. So it's good to see so many people still here sticking with us. Thanks very much. And last but no means least, then we're on to our analytical science theme. So without further ado, let's jump straight in. I'd like to invite Quentin Ramasse to the stage.
Great, thank you. Thank you very much. Thank you very much for the invitation. Thank you, all of you, for staying to the bitter end and the last couple of talks. I'm lucky in a way that I'll be talking about microscopy, so I can start with a few pretty images to sort of soothe the atmosphere a little bit and then build slowly into slightly more complicated things as we go along. And hopefully I'll get into what I really want to talk about, which is those single atom material problems that we can tackle with modern electron microscopy. For once, I don't have 50 people on the slide, but I should be thanking more than 100 people for all their contributions. I'll try and mention their names as we go through. Hopefully, I don't forget anybody. Forgot, I should just click on this. Great, so we're all pretty familiar with electron microscopy, but I'll be talking about a slightly different flavor than you might be used to, and the way I usually describe it, scanning transmission electron microscopy, is something everybody's familiar with, which is SEM. I've seen a lot of SEM images in a lot of the talks today, but put on steroids. And we're particularly lucky to have had those steroids invented for microscopy, if I can put it that way, in the late 90s, and that resulted, as I show up here, into the Kavli Prize being given to those four distinguished gentlemen on the bottom left. And that leaves us with instruments that are really able to go and poke single atoms and look at all those material science problems at the single atom level. So on a very simple basis, a STEM, or scanning transmission electron microscope, is nothing but a very simple instrument. It has a source of electrons that you send through an electron column and focus onto your sample. And thanks to those aberration correctors that were invented in the late 90s, the size of the electron probe that you can create is the size roughly of an atomic column or a single atom, so 1 angstrom or even smaller these days, all the way down to really low acceleration voltages. So back in the day, 20 or so, or 40 years ago, the only way to get to atomic-sized probes with an electron microscope was to go to really high acceleration voltages, and that was potentially very damaging to materials, in particular those beam-sensitive materials, whereas now you're able to do this with much lower acceleration voltages, down into the 60 or 30 kilo electron volt regime, even lower than that, regimes that you would normally associate with a simple SEM. And as with all scanning probe microscopies or scanning microscopies, the power of that particular technique is really that you go and interrogate one specific position at the sample, one atomic column, one atom, one small location, and then collect as much data as you can out of it. And also you can collect images using imaging detectors, in particular one that would be donut-sized with a hole in the middle, collecting electrons that have scattered from your sample to high angle, and you do that typically through something that would be akin to Rutherford scattering, therefore a process that is sensitive to how heavy the material is that you've actually gone through. So your images are weight sensitive in that they'll look slightly brighter if what you look at is slightly heavier, or not quite as bright if what you look at is less bright. And one of the good examples is shown here, a sample that is rather dear to our heart because we've looked at it for a long, long time, and that's a single silicon atom, this really bright dot here, that's been embedded into a lattice of graphene, so all of the not so bright dots that you see arranged in a hexagonal fashion there are single carbon atoms, graphene, and then one of the carbon atoms been plucked out, and then a silicon atom and impurities basically just replace the carbon atom, and of course you see it like a Christmas light. So that's just on the simple imaging side. We'll go through quite a lot of that. What's really going beyond this, and what I'll be talking about in the second half of the talk, is really the spectroscopy aspects. STEM really is an analytical technique, and the beauty of it is you can look at all sorts of other types of interaction that your electron beam has had with your sample that is gone through. And the one that is particularly dear to my heart is electron energy loss spectroscopy, essentially looking at how much energy the electrons have lost to the sample as they've interacted with it. Most of matter is empty space, of course, but as the electrons go through, they might interact a little bit with the electron cloud or get a little bit too close to a nucleus and exchange a little bit of energy with it. And in doing so, the electron from the beam slows down, changes color, you might want to call it that, or changes energy, and then you can arrange those electrons as a function of how much energy they've lost, and that will tell you a lot about the interaction that has taken place, and therefore a lot about your material. And the beauty of what we can do with these machines these days is the energy with which we can define, or the resolution with which we can define the incoming energy of our beams is now in the 1 milli-electron volt range, typically 4 or 5 milli-electron volts. So you send a beam of electrons of about 60 or 100 kilo-electron volts through your sample with a precision of about 1 milli-electron volt, and you can then determine how much these electrons have lost in energy, or how much of a change in wavelength, or how much of a change in color they've undergone with really, really high precision, which is akin to what you would get in a synchrotron, hence the slightly facetious title of putting a synchrotron in a microscope. It's not a phrase that I've invented, it's something that came from Nick Brown, who back in '97 at the same conference where those aberration correctors were being introduced, suggested that this should be the basis for creating a national facility. And in a rather shameless fashion, I am duty-bound to just advertise very quickly the fact that I work at SuperSTEM, which is the EPSRC national facility for advanced EM in particular, and where we focus on these types of instruments, single atom sensitive stems, and it's a free at the point of use facility. So if any of what I'll show you in the rest of the talk is of interest, or if you have samples that you think might be useful, don't hesitate to contact us and come and play with all of our instruments. I'm not going to spend a whole lot of time explaining all the machines we've got. You can find this on our website. Just to say very briefly that most of the results that you'll see today were obtained on these two machines, bottom left, which is a slightly newer one, 2015 vintage, and a slightly older version, 2006, which still delivers single atom spectroscopy. And one important point that I really should make before I forget is, because these machines work at low acceleration voltage, we need extremely thin samples. So maybe this is something that all microscopists are guilty of. They show you some wonderful images and some wonderful results, and they forget to say, oh, by the way, this is very specific to these 2 or 3 samples. So it's not necessarily true of all the samples in the world. Some samples can be made thin enough. By thin enough, 1 graphene sheet is pretty thin, that's quite good. Bilayer graphene is not bad. You can go to about 10 or 20 nanometers thickness, so you have to really slice through your material to make it thin enough to go and look at all those things at atomic resolution. Once you start looking at bulk and much, much larger structures, then of course that facetious phrase, a synchrotron in the microscope, doesn't quite apply anymore. Maybe you have to go through to slightly different types of interactions with your sample to characterize them. And therefore, one important aspect of our work is making samples thin enough using, for instance, focused ion beam, which we've also got at the lab. So, stating the obvious, structure property relationships, this is what all microscopists do, what all material scientists do, and I always say that when you look at all these themes, you can put a big microscope in the middle and say we can address all of these problems one by one. I don't have time to go through every single aspect of these. I've chosen a few to start with as examples, some of which I'll detail a little bit more than others. And then towards the last 15 minutes of my time, I'll go into the more spectroscopy aspect, and in particular, the milli-electron volt spectroscopy aspect of STEM and STEM yields. But let's start with a few applications in particular on the energy materials side of things. And this is basically just a one-slide summary of all you can do with one of these machines. And there's a whole bunch of paper that was a PhD project for one of our students, Ekin Shimshek, who was looking at absorber layers, copper, indium, gallium selenide absorber layer, photovoltaics, from essentially what is bulk all the way down to the single atom. And I think this particular example encompasses how you can go from even device-sized samples all the way down to the single atom. So Ekin was growing a absorber layers that were actually operational, so making actual devices out of those, copper, indium, gallium selenide, over really large distances. So an image here will show you micron-sized grain structure of these absorber layers. And then zooming down to some of those lines that you could see, which turned out to be stacking faults, or perhaps random grain boundaries that you see in various places, looking at the chemistry of these things at the atomic level, so looking at where the selenium columns or the copper columns, the indium columns would sit, and then figuring out what happens at potential defects. Microscopy is always about symmetry interrupted, so what we like are defects, single atoms, line defects, 1D defects, and realizing that in this particular case, a stacking fault that you see here has no real change in chemistry, just a change in the orientation in the dumbbell in the crystalline structure, whereas that random grain boundary here has a lot more copper segregated to that. And with that information, you can then go back to what the actual property of this particular boundary is by looking at the band gap change across a boundary that has more or less copper within it, and see those changes from about 1.39 electron volt to 1.41 electron volt. So changes in band gap of the order of 10 or so milli-electron volts correlated directly to single atom or single atomic column information that you're able to draw from a device that is functional all the way down to those to those columns. What am I doing on time? Just making sure that I'm not spending too much time. One example that I'll spend a little bit more time detailing, just because it again shows the whole breadth of applications in STEM, is thermoelectric materials. And that's a collaboration with Robert Freer at the University of Manchester and Feridun Azur that's been going on for a long, long time. And it also allows me to show you some very pretty pictures. I really can't stop looking at these things. So in a nutshell, for those of you who are not necessarily familiar with thermoelectric materials, one way to think of it in layman's terms is you want a material that will somehow retain heat and send electricity away. So you somehow, or the other way around, keep the electricity and send the heat away. So you want somehow a material that has different types of conduction properties for heat than it does for electrons. So usually these things tend to go together. So if you increase the conduction, the heat conduction, then your electronic conduction will also increase together. So you somehow want to disrupt that. And one typical way of doing this is with layers or material layers or layered materials or defects. One of the types of material that lends itself rather nicely to all of this are these complex oxides that sort of self-assemble with structure that can be layered depending on how much of a particular cation is present. So if you have deficiencies, specific sites that would be, in this particular case, A site deficient, you can build layers here that would perhaps be good, one might think, for carrying the electrons away, but then somehow if you go to an interruption, that might scatter phonons and therefore keep the heat locally. So that's perhaps a good indication that this could be a thermoelectric material candidate. It turns out that it does work out quite nicely with this one single composition, depending on how you process it, just application of heat really. You go from a structure that has, hopefully it's visible from the back of the room, something that looks like a sort of a dash structure, checkerboard, to those bands that you see, to that rather beautiful A-site deficient structure that was showing you at a slightly larger field of view earlier, and you go from, in simple terms, bad, good, better type of thermoelectric. And the question is, how do you relate what you see in the image at the atomic level to how you understand these properties? So you might say again, if you remember what I was saying, if my atomic column is brighter, surely it's heavier. If it's heavier, well, I've got niobium in the system. That's a slightly heavy ion, so therefore something that is slightly brighter will tell me it's got a little bit more niobium, it's more of the heavier cations in it. But that's not very quantitative, and also because you're still looking through a material that is perhaps 10 or 20 nanometers thick, it's a projection. That's the problem with microscopy. You're looking at projection images unless you have a single layer of atoms. So you need a way to combine all this information together and to relate what you see to the property. So if you just do image analysis, you can realize that depending on where you look, when you have, so inverting the images this time, going from bright contrast, noting where an atomic column is, to black contrast, noting where an atomic column is. It's a different type of image, but you can understand it in inverted contrast fashion. Looking at how, depending on how much intensity there is on one particular column, the surrounding columns are sort of tilted. Again, you understand it reasonably easily. You have something big and heavy, it needs a little bit more space to move the neighboring columns around. That somehow creates a little bit of a distortion in the material. If the neighboring atoms happen to be oxygen, and if you have an ionic materials, that's going to change the local distribution of charge. If you change the local distribution of charge, maybe you change the electronic structure, and therefore you change the conduction property. So you can sort of all relate that together. And seeing that at the atomic level, you can do it in a quantitative fashion, measuring small distortions of the order of tens of picometers, maybe picometer level at the atomic level, and then correlating that with the intensity of the columns, and therefore perhaps with what you might call concentration. Of course, it's perhaps slightly better to do this using spectroscopy rather than just images and contrast, and actually look at electron energy loss spectroscopy that I was telling you about earlier. So one aspect of that is very similar to X-ray absorption spectroscopy. If an electron going through the material loses a certain amount of energy, that might correspond to the amount of energy that is necessary to take one of the core electrons of the material out of its position into the continuum. This is specific to the type of species that you have. Again, it's an absorption spectroscopy very similar to XS. In this particular case, if you lose about 450 electron volts, this is characteristic of titanium, and you can create maps position by position of how much locally you have of titanium, or how much titanium is missing locally. And you create maps like this that show you in particular where all the titanium columns are located, positions where there's more titanium, positions where there's less titanium. If you go one step further, you can also look at what is called the fine structure, and I'll go into a little bit more detail about this in a minute, just to start relating everything together. You notice that depending on where you look across this entire map, there's some changes in the electron energy loss spectrum fine structure, those wiggles that you see, and those wiggles mean something. It's essentially telling you that there's a little bit more intensity at one energy loss than another. In other words, your structure of the empty density of states, remember you take an electron from the core of your material and you sort of promote it to the empty band structure, and that tells you a little bit about the structure of, or the electronic structure of the material that changes locally. And at very narrow energy bands, you can also map locally, and you see here that there's a little bit more intensity from these features around those areas where you have a lot of darker atomic positions, so where you have vacancies, and that all goes back together to what I was saying earlier. If you have a slightly heavier column, or a column with more heavy atoms that displaces the columns around it, that will create some distortions. If that creates some distortions locally, that will change the electronic structure, and therefore you can relate this to the near-edge fine structure. So all of this to give you a little bit of an overview. I want to take a little bit of a step back before going back in at the deep end, perhaps, and say that it's not necessarily all about single atoms or atomic structure. You can also look at slightly bigger things, but still benefit from having those tools and those really fine probes. And that's a particular example that I like a lot, because it goes from the very small to the very big. And we're lucky enough to have collaborators at the University of Münster who bring us meteorites or sections of meteorites. And what they want to understand is what happens to the organic matter that sits in those little pieces of rock that actually fall to Earth, and apply these very same techniques locally with a probe that is small enough that you can see the local variations in concentration, or in electronic structure, or in functional chemistry at the local level. And the way you would sell it to your funding agencies, or the way you make people dream, which is always nice when you do science, is to always say that these little blobs of organic matter that are sort of imprisoned within bits of rock that fall from Earth, onto Earth rather, and have sort of moved around for billions of years in the solar system, might have been the start of life on Earth, just because it is organic groups that are there, and it could have contributed to the primordial soup. So it's always rather exciting to get a piece of rock that looks like this, slice it open, and then find grains that are extremely small that contain carbon, so organic matter, and then try and understand what's happened to those by looking at the chemistry, the functional chemistry, and applying a very small scanning probe going across it. So very briefly, 2 specific examples. Those rocks can have very specific chemistry. Some of it can have a little bit more nitrogen-15 than is present in sort of the background, or a little bit less nitrogen-15, one specific type isotope of nitrogen, than is present in the background. And depending on whether you have more or less, that can tell you when that was formed, where that particular meteorite came from, and you can try and understand what's happened to the functional chemistry within those organic grains. So that's 2 examples showing you the carbon yields, or KH, so again, energy loss spectroscopy, of one that had less nitrogen-15 than background, and one meteorite that had a little bit more nitrogen-15 than background, and showing you that you can relate this to specific absorption bands that the chemist can relate to different types of bonding, and depending on the abundance of these locally, you notice that we can make maps on the order of about maybe 50 or so nanometers. In this case, these are amorphous materials, of course, so we're not talking atomic-sized grains anymore, but nanometer-sized grains. You can understand what the chemistry of the whole thing is, and extrapolate as to how these grains have formed and how the local chemistry is formed. And as a very, maybe an initial pointer to what we'll be talking about later, you'll notice on the bottom side here, another graph that is at much lower energy range. This time, instead of looking at hundreds of electron volts of energy loss, we're looking at hundreds of milli-electron volts energy loss. So at the same position as you can look at the absorption spectroscopy, so carbon KH, excess, or eels, you can also have the vibrational response in the IR range in the same way that you would look at things with a Raman spectrometer or an FTIR spectrometer, but this time with the exact same machine, because you have those extremely narrow incoming energy resolution. And that tells you not only that you can do these things, but also it just confirms that the vibrational response is correlated to what you see in the carbon KH. So your functional chemistry is directly related to what the vibrational spectroscopist would normally use as a main tool to determine this chemistry. But remember, we still have a 1 angstrom probe or a 1 nanometer probe, certainly a very small probe. Just as a very last slide on this particular example, I couldn't really resist showing you that, because that's still probably rather fresh in all our memories. Something like a year and a half ago or so, somebody's driveway was somehow smashed with a piece of rock somewhere in the Midlands, the so-called Witchcombe meteorite, and we're lucky enough to work with the National History Museum, and Ashley King in particular, to look at some of these things. So that's what the driveway looked like, that's what the meteorite looked like, and this is what it looks like once we start slicing it up in our fib. And perhaps it's a good example of as pristine a meteorite as you can get. Normally you find these things that have sort of stayed around in Antarctica in particular. This is where a lot of them are found. But you don't know what their history has been, what the weather's been. In this particular case, we know exactly what the weather was like the day the meteorite fell, and it's as fresh as it gets. Until we get to actual return to Earth missions directly from comets or from meteorites in space. That's coming next. I just wanted to show this because I added this slide saying a synchrotron in a microscope, but the point of that particular example was to actually do both synchrotron work and STEM work on the exact same sample. So we took the very same sample, we sliced it up, sent the 1 fib lameller that was 20 nanometers thick to the synchrotron, and then brought it back to our lab, and essentially we get the similar energy resolution, much higher spatial resolution, and variability across the grains. So I've got about 5 minutes left, which is great because that's what I need, to really delve a little bit deeper into those high energy resolution upgrades. So this is what's been going on in the field for the last 5 years or so, since 2015, getting monochromators. So as the name suggests, you get your energy resolution much, much higher, and also taking a leaf from the bio-EM field, using direct electron detection cameras to reduce noise and improve speed, so that you can get extremely narrow energy losses, but also extremely fast detection of these spectra. So this is what was added to our machine not so very long ago. Just to give you an impression of the size of the microscope, this is about 2.5 meters tall, maybe 3 meters tall, so big, but certainly smaller than a synchrotron, more sort of human size. And you do need a ladder to get all the way up top to put those cameras up. So where do we go with all this? Well, we talked a little bit about core loss. I don't have time to give you all the applications in a slightly lower regime from about 5 to 50 electron volts, but as you might imagine, you can do things like measuring band gaps, plasmonics, et cetera, What I really want to focus on is what happens in that ultra low loss regime, now that we can have milli-electron volt probes with 1 angstrom resolution. And I've mentioned it very briefly. One of the obvious things to do is IR spectroscopy, but there's a whole zoo of new things that you can do, and where it all started is the field of phononics. So plasmonics is looking at how collective excitations of electrons are excited in the materials by your electron probe. You can do the same with phonons. So phonons, again, in a nutshell, would be the exact same idea, except instead of the electrons slushing back and forth, this time it's the nuclei that sort of slush back and forth. So you can go and map out phonon modes, so phonon polaritons, at nanometer resolution across, in this case, zinc oxide cube that was worked on at, not by us, I should say, by Maureen Lagos at Rutgers University. In 2D, even in 3D, so map out all the phonon modes in those materials using the energy resolution that you have. Okay, nice. What else can you do? And I'm rushing through 2 or 3 applications before getting really to the crux of the matter. You can use the fact that in the same way that you have Stokes and anti-Stokes mode in sort of more optical type spectroscopy, you also have gain and gain-loss spectroscopy in the electron microscope. And depending on the height of your loss peak in the milli-eV range and your gain peak in the milli-eV range, you can determine temperature of objects, of nanometer-sized objects, as you scan across by looking at this detailed balance of intensity. So that's maybe your nanometer-sized thermometer. Okay, great. Can you go even further than that? You can. You can actually go towards isotope sensitivity. So we're not inventing anything. Electron microscopy is definitely not the only game in town. All the IR and Raman spectroscopists that I've talked to, when I said, oh, we can actually look at isotopes, I said, yes, so what? We've done that for a long, long time. What's exciting is you can do this somewhat locally on the nanometer scale. So the dream really is to be able to have molecules that are functionalizing, say, a nanoparticle, and being able to say that by looking at the shift in the vibrational peak at the low loss, you can map what there is using core loss spectroscopy, but also detect whether or not one particular molecule was using an isotope or another on the nanometer scale. So let's say you have one of those forests of functionalized surfaces. You can say isotope, no isotope, isotope, no isotope, isotope, no isotope on the nanometer scale. But that's all somewhat small single atoms. What I want to go back to is atomic resolution, and that's the sort of the really last little bit, if I have 2 more minutes, if I may. Just because I've talked about single atoms, nanoparticles, nanoscale materials, I want to go back to looking at very pretty images and very pretty atomic structures, and the one application that I want to talk about for that, or what I want to use as an illustration for this, is graphene heterostructures grown on silicon carbide, just to show you that you can put all of this together, even for somewhat bulk materials, and that's a really exciting field for microscopy going forward. That's just as a little bit of background, that's a collaboration that came to us from Vlado Lazarov at the University of York. He's interested in proximity effects using graphene close to bismuth selenide, and in doing so, just because of the very peculiar electron structure of these materials, you have all sorts of interesting effects when you put these two things together. In practice for us, what that meant was that we had access to samples like this, where we had a substrate of silicon carbide with bismuth selenide on the left-hand side. That particular interface I don't have time to talk about. But in between, we had sandwiched a couple of layers of pure carbon or graphene or semi-standing graphene. And we could grow things that had either, in this case, 3 or 2 or just 1 layer of carbon, depending on how these things were grown. And that gives us a rather neat thing to look at. So if you put everything together, we have the ability to do imaging. Silicon carbide, you can just about see the rather faint graphene layers. Bismuth selenide, of course, bismuth is extremely heavy, so you know exactly which are the bismuth columns. But right in the middle there, looking at doing a map using the milli-electron volt regime, you notice that I'm able to distinguish 4 layers, so the distance between these 2 layers is 2 angstroms, or 2.3 angstroms, so we're doing mapping at atomic resolution, or atomic plane resolution, in the milli-electron volt regime, with perhaps even more than this, because if you notice carefully, the fine structure of that first layer, which is this black layer here, is different from the fine structure of the layer 2, layer 3, layer 4. So you can think of it as saying the vibrational response of the one atomic plane that is sitting next to the substrate, the silicon carbide, is different from the vibrational response of the three next one. And you can actually see that. So this is not chemical mapping, this is actually bond mapping, if you want to think of it. And the reason for this, in a sort of a nutshell, just because I really running out of time, is that first layer somehow is still bonded. It sticks to the silicon carbide below. There's still some silicon to carbon bonds. The further carbon layers as you go above that, they're sort of free to breathe, they're free to move and free to vibrate in exactly as you would expect from any material. And so what you're seeing here, especially that shift towards lower energy losses of the modes that correspond to graphite, this is not because we're picking up something else from somewhere else. This is really a defect mode that is induced by the fact that this layer sticks down, and you're really seeing a different vibrational response from the bonding of just a few sp3 bonds compared to the normal sp2 bonds that you would get in graphite. And we're particularly excited by this because you've really just put everything together with that one atomic probe. Take that one step further, and if I can dream a little bit before I stop talking, carbon-13 and carbon-12 also have different vibrational responses, different modes, so you might actually also be able to map your isotopic vibrational response plane by plane, depending whether you have a layer of carbon-12 and a layer of carbon-13, and add defects and map all this at the atomic scale. Right, with this I really ought to stop, so I'll just go to the last slides, just to remind you again that SuperSTEM is a facility. And although I'm standing here, most of the work has been done by all the other guys who should be thanked for their really hard work. And thank you for listening, staying 2 minutes too long. If there's time for questions, I'll take them. Otherwise, I'll be sitting somewhere at the back.
Thank you very much, Quentin. Stunning imagery. Are there any quick questions before we jump to our last speaker?
I have a small question. You showed the buffer layer, and the one on the right-hand side, what you showed is the density of stress curve, right? In the previous slide.
This slide.
It is the density of stress curve, right? The one that you got on the corresponding the buffer layer, that is the density of stress curve, is that right?
You can think of it as a Fanon density of state. Yes, it actually is an energy loss function. So what you're really seeing is how much energy is lost by the electron, but it is somewhat similar to a density of state. Not exactly, but it's comparable. So if you do calculations, this is indeed what you compare it to, because it's difficult to make the step. The reason it's difficult to make the exact comparison is it's a scanning transmission electron microscope. We have a very high convergence angle, so it's not just one incoming scattering vector or one incoming vector from the electrons and one outgoing scattering vector. You have to do all sorts of integrations, and it gets things a little complex, especially when you tell your theory friends that they'll need to burn their entire allowance of compute hours for the year for the one experiment that you want them to simulate for you.
One short question. The soft X-ray emission spectroscopy, optical spectroscopy, and the electron energy loss spectroscopy of these three, which one will give the accurate band gap?
Yes, I could get into very hot water answering this particular question. The best cop-out the best answer I can give you without making too much of a cop-out is to say that for eels in particular, it's not so much that you have the absolute measurement of the band gap, it's just if you have a comparison or self-consistent comparison, then the changes you see are physical, they're real. What you measure, then there's a whole 2 hours of discussing whether or not this is the band gap and what actually it means to measure the band gap from electron energy loss spectroscopy or from other optical methods. So the comparison one-to-one between, say, ellipsometry and eels might not give you the very same answer, but the physics that will give you changes as you go from across a defect, for instance, will be the same, and therefore that is what you try and understand, not necessarily the absolute value. Likewise anyway, because DFT, or even if you go beyond DFT, will struggle to give you an absolute value regardless, so it's always about trying to understand what's the defect that you're interested in changes in your material.
Okay, I think any more questions need to be taken offline. We need to move on. Thank you very much, Quentin. So I'd like to invite our final speaker, Alison Macente now, please.
Hello, everybody, and thanks for sticking around to the end. So today I'm going to take you through a journey through kind of geological time and inner space, and I'm going to show you how we can see what we cannot see. So I'm going to briefly introduce you to non-destructive imaging techniques, and I'm going to show you some case applications, and then I'm going to end by talking to you about the facility in our school. So when we look at an object in the laboratory or in our everyday life, what we see is a frozen snapshot of the geometry of that object. And we don't really have any information about what the geometry looks like inside, or what was the process that led up to that microstructure. So it's essentially a black box. And as we learned in the past few talks, changes in the microstructures actually are quite important because they can drive changes at large-scale behavior. So my research focuses around using non-destructive imaging techniques to monitor and quantify the evolution of microstructural changes under dynamic conditions, such as temperature, load, or fluids, and see how these can affect large-scale behavior. So what are these non-destructive imaging techniques? Okay. So one of these is called X-ray computed tomography. It's an X-ray technique that allows us to investigate the internal characteristics of a sample without physically the need to cut it. And the way it works is in a laboratory setup is that we have not really working. We have an X-ray tube where we have a large potential difference coming from a tungsten filament that generates an electron beam. And this electron beam hits a metal target. And when this happens, we have to generate, sorry. Okay, so we have the generation of X-rays. These X-rays irradiate a sample that is positioned at, in a rotary stage. Yeah, not working. And on the other side, we have a detector that collects the X-rays as they move across the sample. And they are recorded, they are converted into photons of visible light, and they are recorded in what we call a 2D radiograph, which is essentially the same radiograph that you have when you X-rays your broken arm. And we collect as many radiographs as we can over 360 degrees rotation. And in doing so, we are able to create a 3D model of our sample. And the images that are reconstructed through this process are in gray base intensities, which means that very dense material will appear bright because they interact a lot with the X-rays. And very low density materials such as porosity or organic matter will appear very dark. So if you were to slice this orange open, this is what it looks like. You can recognize the internal slices of the sample. You have some internal porosity, and then you can recognize the bumps on the outer skin. So now that we know how these techniques works, let's have a look at some case application. So the first one is, I'm going to talk about CO2 sequestration in natural rocks. We all know how it is important to mitigate carbon emission in the atmosphere. And one way that geoscientists do that is by trying to capture the CO2 in the atmosphere and store it safely in the subsurface. And this is called CO2 sequestration. And in order to do so, we need rocks. They are very abundant, and they have a certain amount of voids and permeability, which allows the CO2 to flow freely through the rock. They need to be impermeable because we want to avoid leaching of toxic elements, and they need to be highly reactive in order to form carbonate minerals through what we call in situ mineral trapping. And one type of rock that is really an excellent candidate is basaltic rocks. Basalts are, okay, without going into too much details, they are rocks that are formed with rapid cooling of lavas. And they constitute up to 10% of our Earth's surface, so they're very abundant. They're often cut by impermeable materials, and they're very reactive, which means when they combine with the CO2-rich fluids, they form these sort of carbonate-rich minerals. And this is what they look like under the microscope. So when this process of CO2 sequestration happens, the properties within the rocks change a lot, especially porosity and permeability. So in order to assess the CO2 potential of these rocks, we first need to understand how these microstructure properties change over time. And one way we can do that is by applying X-ray computer tomography. In this case, I apply this technique to a type of basalt that is called amygdaloidal, because during the cooling, air got trapped inside, and it was later filled. CO2 fluids infiltrated the rock, and they essentially mineralized this type of carbonate mineral, which is called calcite. And I did this as an analog to CO2 injection into basalts. So these are images that we got from the XCT. It's a vertical slice through the 3D model, and we can recognize the basaltic matrix. But what's most important, we can recognize where the voids filled with air were, but they're now filled by this dark gray color, which is calcite. And then we still have some black material that is the air-filled porosity, and some fractures going through the rock here and here. And these fractures are quite important, as we will see later on. So how can we quantify how the calcite modify the porosity of the rock? We can employ an algorithm that is called digital backstripping. And essentially what we can do is take all the calcite that is now filling the material and essentially try to digitally remove it to make in reverse calcite precipitation. So how does that work? So we take all the porosity that we have now in our rock, and we define what we call the surface connected porosity. So that is all the void content that is connected wall to wall along a specific surface, in this case, this direction, the Z direction. And then we dilate it by a certain amount of voxels, so a 3D pixel, until we simulate calcite dissolution. And we tend to do this in steps, so we go from T0 to T1 and T3 until all the calcite is removed. And at every time step, what we can do is calculate the percentage of connected porosity over the total amount of porosity. So let's have a look at some of the results. One way to simulate calcite dissolution is by assuming that at every time step, we remove the same amount of material. So what we can quantify, for example, without going into too much details, is that you can plot your relative time on the x-axis and the percentage of connected porosity on the y-axis, and essentially you go from left to right with the backstripping, and you see with this digital dissolution, the amount of percentage of connected porosity increases over time. But that's not the only thing that you can do. For example, we are able to see that along the x direction, which is these dashed lines, the porosity is more connected, whereas in the other two directions, they basically start at zero until we have enough void to reconnect the porosity. But I'll show you this in better details. If we have a look at these 4 time steps, what we can do is that we can look at the 3D geometry of these voids. So for example, in the x direction, what we see is that the amount of percentage connectivity greatly increases when we start filling in blue, essentially reconnecting the voids over time. Whereas the other two directions, they start disconnected, and then eventually they will reconnect. We can also do the opposite. So let's say we start from the last stage of the geometry, and we say, okay, what happens if I simulate digitally an event of precipitation? And what we can see is essentially a similar process. Just in this case, we go from right to left, and we simulate calcite precipitation. And what we see is that for the x direction, the process is quite slow, indicated by a low gradient of this curve, whereas in the other two directions, this is quite fast. So why is that happening? So if we have a look at these 4 time steps, what we can see is the horizontal axis in this case is the x direction. We see from the start to the end of our process, we have the presence of this flat surface, which is a 3D geometrical features that remains present until the end of the process. And that flat surface represents our fracture network. So what that means in terms of permeability, what does that mean in terms of permeability? So we also calculated permeability through some simulation. And what we saw is that when we first tried to dissolve the calcite, as you expected, during the first time steps, we greatly increased the permeability from 2 to 32 millidarcy. And that is because, if we have a look at our 3D geometry, is that because immediately we dissolve big pores. So the calcite in them was quite big. If we do the reverse and we look at what happens during precipitation, what we see is that within 1 time step, the permeability immediately dropped to something very close to 0, and it stays constant after that. And we calculated that that very low value, oops, not showing, yeah, is actually dictated by the microfracture network. So if we have a look at the 3D rendering, what that means is that within 1 time steps, we immediately close off these connections and remain just the fracture network. So it means that during the later stage of precipitation, the permeability is controlled by this very narrow microfracture network. So in terms of assessing the CO2 storage potential of these rocks, we need to carefully consider whether microfractures are present and how these may impact the overall CO2 flow through the rocks. So as a first take-home message, we can say that digital backstripping, together with, for example, simulation and actual quantification of precipitation rates, can help us to gain insights into what happens during in situ mineral precipitation. So that's one way to use XCT. The other way is to actually go try to reproduce a process in the laboratory. And this brings me to the second case study. This is a study I did during my PhD, in which I was trying to reproduce a geological process in a laboratory setup. So without going into too much geological terms, there are some processes happening in Earth through which we basically have dissolution of material where grains are stressed and loaded to each other, and they are surrounded by a thin layer of fluid, and the material gets transported and it will precipitate into the nearby pore space. And what that means is that it greatly influences and affects how the porosity and the permeability of the rocks looks like, which means it affects how mass transport of fluid flow occurs. So it's really important to understand how these processes occur. And nobody has ever imaged this process before, or at least not to this length scale. So in my laboratory experiment, I used salt as rock analog to accelerate the process, and not because a PhD is only 3 years long. So these light gray are salt grains, and these are vertical slices through the microCT data set. And then in my second sample, I used salt and what we call biotite. A biotite is a phyllosilicate mineral. And I use this because the process in other experiments has been shown to be greatly accelerated in the presence of this mineral. But again, we don't really know how or why. So what I was able to do is, over the course of 4 months or so, I was able to load these samples and monitor their evolution over time. These are 4 time steps over 4 months of experiment. And as you see, the samples are compacting over time, the grains are fusing to each other, and the overall black content, which is the porosity, is also reducing over time. So we can really say that with the microCT, we can actually watch the process and monitor the evolution of this process over time. But what is also happening is that when we have the presence of these white grains, which are the biotites, the porosity is actually greatly reduced. And if you look very carefully, we have the formation, we have way more salt grains nearby the white particles. So what does that mean in terms of pore connectivity and permeability? So we can employ some image analysis algorithm, which are called cluster analysis. And what that does, it basically assigns a color and an identity to each connected pores in this case. So these are free data set taken from across the compaction curve here. And this is the first sample. So the presence of mainly blue color indicates that the porosity remains pretty much connected over time, and only disconnected towards the end, but with very minor effects. But when we look at the second sample where we have the biotite, we can see that already halfway through this experiment, about here, the porosity, the pore connectivity is greatly disconnected. And that is because these phyllosilicates not only accelerate the process, but they can really sort of create a barrier to fluid flow. So, second take-home message is that XCT can help us to understand what are the microstructural properties that drive changes in the large-scale behavior. So next up, I'm going to talk to you about some other application which you might want to use XCT. In the research group I'm currently part of, we use XCT to monitor the evolution of microstructures in low-carbon cement. And we do this because we are trying to assess how different types of cements with low carbon how the pore structures actually controls their mechanical strength. So it's really quite important that we monitor this over time for durability and sustainability. XCT has been used a lot also in industry manufacturing, and there was another talk about it, and for example, 3D printing and so on. So for example, this is a piece of satellite part, and it has some welded metal. I don't know if you can see the two metals here. And the black dots that you see, these are defects, they are voids. And essentially, this part failed because these voids are essentially driving changes at the large scale behavior. So it's really quite important to check these materials. We can also use it in meteorites, for example, like the previous talk. Why do we do that? Well, essentially, the spatial distribution of each mineral phase in meteorites and how they are connected or disconnected and so on can tell us a bit more how they form and where they may have come from. So it's really also quite important. We can also use it for a bunch of other applications, forensic anthropology, a lot of archaeology. I've collaborated with the National Museum of Scotland to look at some artifacts of this Viking horde that was on tour, I think last year or the year before. So it's really quite fascinating. But it can also be used in medicine. At least we actually have a lot of medical CT scanner. In this case, we were looking at, defects in a high surgery blades. And just a quick slide about the facility in our school. So we have a Zeiss Versa 410. What that means is that we can do normal tomography, but we can also do internal tomography because we have 4 optical lenses, so we can actually scan very small objects with high resolution. And we can couple it with what we have, it's called an in situ rig, that has the potential to load your sample and do tension and do also temperature changes, so for freezing and thawing experiments. And last up, we also have an environmental SEM. What that means is that we can do environmental studies for very large samples. So we're really up for business to anybody. So if you want to know more about it or are interested in use it, just please come and talk to me. And I would like to thank all the co-authors and the collaborators that I have the pleasure to work with over the past few years. Thank you.
Thank you very much, Alice. If you want more information from Alice, then hopefully she can talk to you over drinks. I think we can take one quick question and then we really need to do our closing remarks. Jim.
Thank you very much for the interesting talk. I have a question about the way in which the data is analyzed. So you presented an assumption that calcite dissolution or precipitation happened linearly with time, I'll call it a layer at a time, but you know what I mean, right? It's a constant rate of removal or addition. I mean, I don't believe that that's probably the case, but I would have thought you would use the data the opposite way to ask the question, does it get removed preferentially at certain sites and how do the rates differ? Did you also look at the data that way? And if not, why did you decide to use the assumption that you did?
Yes, no, that's a great question. And I do have the answer to it. It wasn't included in talk because of the timing, and I was focusing more on different applications. But there are different ways to model the backstripping and to simulate different rates and mechanisms. And that is still like a simplification of the actual process happening in nature. The next step that we're already working on is modeling the precipitation or dissolution according to real rates. And that means basically taking into account, for example, where the flow flows faster, for example, in narrow pore throats. And then combine that with other experiments as well. So, and there are, XCT has been used a lot to also do experiments by injecting CO2 into the pore geometry, but that wasn't just the focus. So I hope that helps with the question.
Okay, well, if you'd like to join me thanking Alice and closing our final session. Whew. What a day. That was a fantastic day. So it just remains for me to introduce or bring back to the stage Edmund to close the exchange.
Thank you very much indeed, Andy. I think just as we come to the end, just a few thank yous are in order. Firstly, thank you to all the speakers today and all the posters. They would be all fantastic, and I'm sorry we just don't have another 2 days to go and look at them all or more detail, because they've really been great. So can I thank everyone, and can we all thank each other for all the posters, talks, and everything else? I think moving on in my thank yous, then I think there's a team of 4 people that we all need to thank very much indeed, who are dotted around, 2 of them sitting down here, Andy and Lucy. Dan, I think, is downstairs. Helen is here. Someone said to me, what do you have to do? And I said, I have to do absolutely nothing for this. It all seemed to happen, and it's absolutely true. All I had to do is give me a microphone at some point and say a couple of words. Everything else has been sorted by this team, and really, thank you so much for today, yesterday, and tomorrow with the External Advisory Board. Thank you for all the arrangements you've made. A couple of other thank yous while we're there. Obviously, it's great being part of the Bragg Centre and having everyone working together. I think we also need to thank the Royce Institute, which partly funds quite a bit of what we do. So a thank you to the Royce Institute. And for those that want to know more about the Royce, any of the Bragg team, I can tell you plenty more about it, so come and catch us over a drink or at any other time. And I'd also like to thank, a lot of this has been arranged between us and also the university. I think it's conference, or is it university conference, if I got the right terminology there? I have. But, they have worked really hard. That we've had the food they've provided, the arrangements, being around to help us all day. So although I don't know we've got representatives in the building now, I think a thank you to all the university who've really helped put this together. And just continuing, sorry, it's very boring, but it's really important. And also we've had the team at the back here. I'm not sure, since they're pointing straight at me, how much I'm thanking them. But anyway, a big thank you for doing the live streaming today. I don't know how many we've got on and had through the day, but we had 50 at the start of the day, I know, watching the live stream. And I hope those watching the live stream have really enjoyed it. And thank you for those who put this together and made it so professional, because I've seen some of it. So thank you very much indeed. Okay, we're almost there, but the last person I want to thank is, we've had the External Advisory Board who've joined us throughout this, and they always give us invaluable advice, and we always wait for the day afterwards when we have the feedback from the External Advisory Board of what they say. But since the Bragg Centre started, the person who's chaired the External Advisory Board is Dame Professor Julia Higgins, who's sitting at the front here, and she's done an absolutely magnificent job in trying to guide us, help us, steer us, encourage us all the way through it. So Julia is stepping down at this meeting now, and really from all of the University of Leeds and the Bragg Centre, Julia, we thank you immensely for all you've done to help in the years as we try to work out what we should be doing as a centre, how we might do it, and those gentle guidance and those words of encouragement have really been invaluable to all of us. So, Julia, thank you very much. So I think Julia is kindly going to say a couple of words now, but she's going to come in the front, so again, captured on camera. And then, yes, I felt, oh gosh, when the capture on camera. And then once we've done that, there's a few poster prizes to give, but you're going to have to wait to the end for that. Otherwise, so that's the last thing we're going to do before we then go to get some more drinks. I will stand by you, Julia.
You want me to hold that, right? Well, I have been thinking very much of the last, essentially nearly 5 years. I first came to Leeds to talk to the then Deputy Vice-Chancellor, I think she was, about what the Bragg Centre and whether I would consider chairing the External Advisory Board in June 5 years ago. So it's been an interesting trip and never boring. And I've been very much thinking today how much has changed, but always in a direction for the better. In the middle, we had COVID, quite extraordinarily. We, the External Advisory Board, managed 3 meetings face-to-face and then 4 virtual ones. And we came back together last June for the opening of the building, which was a splendid occasion, which we all enjoyed. And now I'm going to hand over to somebody else, I hope. Otherwise, there'll be a vacuum. And of course, we have a discussion tomorrow. There are too many things to mention that have changed, but just the success of a meeting like this, which we might have hoped about it 4 years ago, but we couldn't possibly have known. There have been so many interesting discussions at the advisory board meetings and the interactions between, like deciding what your mission is, what your vision is, and some of them are going to continue changing. I'm sure this place is not going to stand still. But the university had a vision, and it didn't quite know what was going to be at the end of the vision. We're not at the end of the vision yet, but I think everybody involved believes that things have moved fantastically, and a success story is unfolding here, the success story of the Bragg Centre. And I don't really want to say any more, except how much I've enjoyed working with the team here, which has changed over time, with all of the members that we've interacted with, the EAB members who've been hugely supportive and responsive. I send out an email saying, I need you to reply by the end of the week, please. And people always do, and send in helpful comments. Everybody's been involved. It's been a very great trip, and I look forward to a drink with everybody tonight and to my last involvement with the discussions. I kept finding myself during this week thinking, next time, and then thinking, no, it's not your job next time. So thank you, all of you, and thank you to the university for letting me do this job. I really loved it. Thank you.
So people were voting for posters and looking at posters. There was an enormous number of really good posters. We said we'd give 1 first prize and 2 second prizes. In fact, we decided that we would give 3 second prizes, but that means you haven't got the official certificates yet today, and we haven't got quite a number of prizes to give, so we're going to have to come back to that. But what I'd like to do is the 3 runners-up, I think if you all can come up together, we've got a temporary certificate for you, and then we'll sort out a proper certificate and a proper prize for each of you, maybe not tomorrow, but quite soon. So the 3 are Thomas Barber, Francis Dent, and Manoj, and I don't think I'm going to read out Manoj's surname quite right from reading it here. So Manoj, and then Francis, and Thomas, and hopefully some of you are here. There's my Okay, right, I think what we'll try and do is just get a photograph of everyone together if we can. Oh, me as well. Me. And then the winner was Nora Al-Rafai. Nora, are you here? Thank you very much. And can okay, and so those are the other bits. So I thank you all very much. I think all the posters, if we could give them 62 poster prizes, we would be glad to do it. They were really very, very good. So thank you all very much again. And I think, if I've got this right, we're now heading up. I've got the microphone, have I? I think we're heading back to the refectory where I think there's some drinks, and those who've still got their posters up, we can go and look at those. So thank you very much, everyone. And I'll bring this day to a close for the formal bit. So thank you very much indeed.